Imagine standing at the very edge of Earth's atmosphere, where the blue sky fades into blackness and gravity loosens its grip. One more step and you're no longer bound to our world. You've crossed into space, a place of endless silence and chilling mystery. But here's the real question. What comes after that? What lies beyond the edge of space? Is it just more stars, more galaxies? Or is there something truly that defies the rules of physics, time, and imagination? Before we begin, let us know where in the world you're watching from and what time it is for you right now. Drop it down in the comments below and settle in for a fascinating journey through space. To truly understand the mind-blowing discoveries made by the James Webb Space Telescope, also known as JWST, we first need to travel all the way back to the very beginning of everything, the birth of the universe itself. This incredible moment is known as the Big Bang. But don't picture a typical explosion, like fireworks or a bomb. The Big Bang was something entirely different. It was the sudden and unbelievably fast expansion of the universe from a single point that was unimaginably small, scorching hot, and densely packed with energy. This cosmic event happened around 13,800 million years ago, and it wasn't just the beginning of the universe. It was the moment when space, time, and all matter burst into existence. In the first few seconds after the Big Bang, the universe was like a stormy sea of energy, filled with tiny particles zipping around in every direction. It was so incredibly hot, hotter than anything we can imagine, with temperatures reaching trillions of degrees, that atoms couldn't even form. Everything was pure chaos, with no stars, no planets, and no galaxies, just glowing, blinding energy. For hundreds of millions of years, the universe stayed in this strange state. Slowly but steadily, it expanded and cooled down. Then, something extraordinary happened. Around 400 million years after the Big Bang, the first atoms came together, mainly hydrogen and helium. These simple gases were pulled together by the force of gravity, and as they clumped together, they heated up and ignited the very first stars. These newborn stars didn't shine alone. They gathered into the first primitive galaxies, lighting up the darkness of space and creating what scientists call the cosmic dawn. This was a magical era when the universe was beginning to form its first structures, and this is exactly the moment in time that the James Webb Space Telescope is now peering into. It's capturing breathtaking pictures and precious data from when the first galaxies were just starting to glow, helping us uncover the mysteries of our universe's earliest days. The James Webb Space Telescope is unlike anything humans have ever built. It was launched into space on the 25th of December 2021, a cosmic Christmas gift to humanity. But JWST doesn't orbit the Earth like most satellites. Instead, it travels around the Sun, parked at a special spot called the Second Lagrange Point, or L2. This point is about 1 million miles away from Earth. It was carefully chosen so the telescope could stay stable and far away from Earth's heat and light, giving it a crystal clear view of the universe. What makes JWST truly special is its ability to see the universe in a kind of light our eyes can't detect, infrared light. While visible light is blocked by clouds of cosmic dust, infrared light can sneak through, revealing hidden stars, galaxies, and other objects that other telescopes can't see. This is especially important for studying the oldest and most distant objects in space. As the universe expands, the light from faraway galaxies gets stretched into longer, redder wavelengths. This stretching, called the cosmological redshift, turns visible light into infrared light. Because JWST is designed to detect this faint, stretched-out infrared glow, it can look farther into space, and farther back in time, than any telescope before it. It's like having a time machine that shows us what the universe looked like more than 13,500 million years ago, just a few hundred million years after everything began. When JWST sent back its very first images, scientists were amazed. The telescope had looked deep into the ancient past and captured pictures of galaxies forming only a few hundred million years after the Big Bang. This was the universe's baby stage, and yet it was already full of surprises. Astronomers expected to find only a few tiny galaxies, but they found far more than they had imagined. These early galaxies came in all kinds of strange shapes and sizes, much different from what scientists expected. It turned out that the early universe was more lively, more crowded, and more chaotic than anyone had guessed. One of the most exciting things JWST discovered was the presence of proto-galaxies. These were the first clumps of stars that would eventually grow into the massive galaxies we see today. But they didn't look neat or orderly. Instead of smooth spirals or round shapes, these early galaxies were messy, clumpy, and wild. New stars were being born at an incredible pace, with entire clusters lighting up in bursts of energy. This discovery challenged older ideas that galaxy formation was slow and gentle. JWST showed us that the early universe was full of energy and drama, changing our entire view of how the cosmos took shape. JWST also brought us closer to finding the very first stars ever formed, called Population 3 stars. These stars were unlike anything we see in today's skies. They were made from the purest ingredients left behind by the Big Bang, mostly hydrogen and helium, without any heavier elements like carbon or oxygen. Because of this, scientists believe these stars were huge, far larger than our Sun, and burned extremely hot and bright. But they lived fast and died young, burning up their fuel quickly and exploding in massive blasts called supernovae. Some of these explosions were so powerful that they became rare events called pair instability supernovae, the most intense explosions in the universe. When these ancient stars exploded, they scattered heavier elements into space, which later helped form new stars, planets, and even the building blocks of life. By uncovering clues about these long-gone giants, scientists are slowly solving the mystery of how the universe grew from simple beginnings into the rich, complex place we live in today. But JWST doesn't stop at looking into the distant past. It is also helping scientists understand two of the biggest puzzles in the universe: dark matter and dark energy. These strange forces make up about 95% of everything in the universe, yet we can't see or touch them. Dark matter doesn't shine or give off any kind of light, but we know it's there because of the way it pulls on galaxies with its powerful gravity. JWST helps detect dark matter by watching how it bends the light from galaxies behind it, a trick of nature called gravitational lensing. This lets astronomers map where dark matter might be hiding and figure out how it helps shape the structure of the universe. Then there's dark energy, which is even more mysterious. It's a force that's causing the universe to expand faster and faster over time. By measuring how quickly galaxies are racing away from us, JWST gives scientists new clues about how dark energy works. These discoveries are incredibly important, because they might help answer one of the biggest questions of all. Will the universe keep expanding forever, or will it eventually stop and collapse? JWST is also on the hunt for something even closer to home: life beyond Earth. One of its most exciting missions is to study planets outside our solar system, known as exoplanets. Some of these distant worlds may have just the right conditions to support life. Using its advanced tools, JWST can examine the gases in a planet's atmosphere and look for special chemical signs that might hint at life. If it finds water vapor, that could mean the planet has clouds or even rain. If it finds methane, it might come from volcanic activity, or maybe even microbes. And if it finds lots of oxygen, scientists will start to wonder, could there be plants or alien life forms producing it? Just imagine the moment when we finally find proof that we're not alone in the universe. That would change everything we thought we knew. However, the James Webb Space Telescope is much more than a camera in space. It is a window into the deepest mysteries of time and space. It has already confirmed some theories and shattered others. One of its most surprising discoveries is that fully formed galaxies seem to appear much faster than anyone expected. According to older theories, it should have taken billions of years for galaxies to slowly grow and develop. But JWST is showing us galaxies that came together in a cosmic blink of an eye. This means scientists might need to rewrite major parts of our understanding of the universe. One of the most surprising discoveries made by the James Webb Space Telescope has to do with the huge black holes found in the centers of some of the oldest galaxies ever seen. According to what scientists believed before, these black holes should have been small, because there simply hadn't been enough time in the early universe for them to grow so large. But the James Webb Space Telescope has spotted black holes that are much bigger than expected. This means that black holes might form and grow much faster than scientists ever imagined. It's a mystery that challenges everything we thought we knew about how black holes begin and how they evolve over time. These strange and unexpected findings show us that the universe is still full of secrets, and thanks to the incredible technology of the James Webb Space Telescope, we're only beginning to discover what's out there. Now, let's pause for a moment and take a closer look at the amazing machine behind these discoveries. The James Webb Space Telescope, often called JWST, is one of the most advanced tools humanity has ever sent into space. It has a massive mirror covered in gold, which stretches more than 21 feet across. That's about the size of a small house. This mirror was specially designed to collect the faintest rays of infrared light coming from faraway galaxies. But what makes it even more fascinating is how it's built, not as one single piece, but from 18 golden hexagon-shaped segments. These pieces unfolded like petals in space, creating a beautiful pattern that looks like a giant golden flower blooming in the darkness. But JWST's power doesn't stop with its giant mirror. It's loaded with advanced instruments, like powerful cameras and spectrographs. These tools don't just take pictures, they analyze light in incredible detail. They can break down the light from stars and galaxies that are millions or even billions of light years away. By studying this light, scientists can learn what stars are made of, how they're moving, how old they are, and much more. It's like doing archaeology, but instead of digging into the Earth, scientists are digging into the ancient history of the universe, uncovering stories written in light that has travelled across space and time for billions of years. The James Webb Space Telescope is more than just a brilliant piece of engineering, it's also a symbol of international teamwork. While the project was led by NASA, the space agency of the United States, two other major partners helped make it possible: the European Space Agency and the Canadian Space Agency. The European Space Agency provided important scientific instruments, and the Canadian Space Agency added high-tech equipment and funding to help the mission succeed. This global partnership shows what humanity can achieve when we work together. Scientists, engineers, and dreamers from all over the world joined forces to build something truly extraordinary. The JWST proves that when people unite around a common goal, like exploring the universe, we can reach new heights and make discoveries beyond imagination. Looking at what JWST has already found, it's impossible not to feel excited about what's still to come. The telescope is gathering so much valuable data that scientists will be studying it for many years into the future. These discoveries will inspire new generations of astronomers and scientists to keep asking questions and to keep pushing the boundaries of what we know. And JWST is just the beginning. In the coming years, more amazing space missions are getting ready for launch. One of them is the Nancy Grace Roman Space Telescope, which will give us an even wider view of the cosmos. Another is the European Extremely Large Telescope, a giant observatory being built on Earth, which will give us incredibly sharp views of distant galaxies. All of these tools will work together, helping us uncover even more secrets about the universe, how it started, how it works, and where we fit in. These efforts are about more than just science. They're also about human curiosity, the drive to understand where we came from, and the deep connection we feel with the stars above. Every mission like JWST helps us feel a little closer to the universe and a little more connected to each other. The James Webb Space Telescope has already changed the way we see the universe. By looking back over 13.5 billion years into the past, it's giving us a view of the cosmos as it was just after the Big Bang. The universe is unimaginably vast, stretching out farther than our minds can fully grasp. For thousands of years, people have looked up at the night sky, wondering where it all began and how it came to be. Over the last few centuries, scientists have worked tirelessly to solve the mysteries of the cosmos. They've asked big questions. How did the universe start? What has happened to it over time? One of the most fascinating clues to answering these questions comes from something called redshift. Though it might sound like a science fiction term, redshift is a real and powerful phenomenon that helps scientists understand how the universe has been expanding ever since it was born. To understand what redshift is and why it matters, we first need to talk about light. Yes, the same light that shines from a flashlight or the sun. Light moves in waves, just like the ripples you see when you toss a stone into a calm pond. These waves come in many different lengths. Some waves are short and others are long. The length of a light wave is what gives it its colour. Shorter waves look blue or violet, while longer ones appear red. Now, here's where things get exciting. When scientists study the light coming from stars and galaxies, they look very closely at those waves. By measuring how long or short they are, they can learn all sorts of things, like what the object is made of, how far away it is, and even how fast it's moving. Redshift happens when those waves of light get stretched out during their long journey through space. When the light's stretched, its waves grow longer and begin to shift toward the red side of the colour spectrum. That's why we call it redshift. Think of it like this. Imagine a car zooming past you. As it comes closer, the sound it makes is high-pitched. But as it speeds away, the sound drops to a lower pitch. This is called the Doppler effect, and it doesn't just happen with sound, it also happens with light. When a star or galaxy moves away from us, the light it gives off stretches, and its colour shifts toward red. In space, this redshift tells us that galaxies are moving away from us, and not just a little bit. Some are racing away at incredible speeds, and the farther away they are, the faster they seem to be fleeing. That's where redshift becomes incredibly important. By measuring how much the light from a galaxy is redshifted, scientists can figure out how fast that galaxy is moving and how far it is from Earth. This discovery changed everything we thought we knew about the universe. Back in the early part of the 20th century, in the year 1929, an American astronomer named Edwin Hubble made a groundbreaking observation. While studying distant galaxies through his telescope, he noticed something truly astonishing. Every galaxy he looked at seemed to be moving away from Earth. And not only that, the farther away the galaxy was, the faster it was moving. From this, Hubble came up with what is now called Hubble's law, which says that the universe is expanding. This means that space itself is stretching, like dough rising in an oven. The galaxies aren't flying through space, they're being carried farther apart as space itself grows. This was one of the biggest clues that helped support the Big Bang theory, the idea that the entire universe began from one incredibly hot and dense point around 13.8 billion years ago. Since that moment, the universe has been growing, and redshift is one of the ways we can track that growth. Whenever scientists detect redshifted light coming from a galaxy, they can estimate how far away that galaxy is, and more incredibly, how long ago that light started travelling toward us. In fact, the more redshifted the light, the longer it has been journeying through space. This means that redshift doesn't just tell us about distance, it lets us look back in time. Imagine this. When we observe a galaxy that is billions of light years away, we're seeing it as it was billions of years ago. The light from that galaxy has taken a very, very long time to reach us, sometimes more than 13 billion years. So, in a way, telescopes are like time machines. When we detect strong redshift, we're not just seeing how far away something is, we're seeing how it looked when the universe was still young. The galaxies with the highest redshifts, the ones furthest from us, show us what the universe looked like only a few 100 million years after the Big Bang. These galaxies are incredibly valuable to scientists because they offer a rare peek into the universe's early days. Back then, everything was different. Space was hotter, denser, and packed with more raw materials like gas and dust. The first stars and galaxies were just beginning to form, lighting up the cosmos for the first time. Studying these early galaxies is like peeling back the layers of time. Every new discovery helps us understand how the universe changed from a tiny, blazing hot point into the gigantic and complex structure we see today. To study these faraway galaxies and their redshifted light, astronomers use extremely powerful telescopes. The Hubble Space Telescope, launched in the year 1990, and the newer James Webb Space Telescope, launched in December of the year 2021, have been essential for this mission. These space telescopes can see incredibly faint light coming from galaxies that are located billions of light years away. Light so dim and ancient that no ordinary telescope could ever detect it. When scientists examine the light from these distant galaxies, they measure exactly how much it has been stretched. The more it's stretched, the higher the redshift, and the older the light is. This allows astronomers to map out the history of the universe, piece by piece, light by light. So what do we see when we look at these high redshift galaxies from the early universe? Surprisingly, they look nothing like the big, beautiful spiral or elliptical galaxies we see today. These early galaxies were small, clumpy, and often strange in shape. They were still being built, still forming stars and still gathering gas and dust to grow. Many of them were crashing into each other and merging, huge cosmic events that caused bursts of star formation and reshaped their structures. Over billions of years, these early galaxies slowly grew larger, calmer, and more organized, eventually turning into the majestic galaxies we see in the modern universe. But by studying them in their youth, through the redshifted light they left behind, astronomers can learn how galaxies grow up, how stars are born, and how the universe itself has evolved over time. One of the most exciting things about studying galaxies that are extremely far away is that they let us look deep into the past, into a time when the very first stars in the universe were born. These first stars are called population 3 stars, and they are unlike any stars we see today. Scientists believe they formed shortly after the Big Bang, a time when the universe was still incredibly young and everything was made mostly of two very simple gases, hydrogen and helium. Back then, the universe was a quiet, dark place, filled only with these gases floating in all directions. But slowly, over millions of years, gravity started to pull the gases together, squeezing them tighter and tighter. Eventually, this pressure caused the gas clouds to collapse, and that's when the first stars burst into life. These early stars were massive, many times larger than our Sun, and they burned much hotter and brighter than anything we see today. But they were missing something important. They didn't have heavier elements like carbon, oxygen, or nitrogen, which are essential for creating life. Instead, they were made almost entirely of the two lightest elements, hydrogen and helium. When these giant stars finally reached the end of their lives, they exploded in powerful blasts called supernovae. These explosions were incredibly violent and spread newly created heavier elements into space, elements that didn't exist before. It was only through the deaths of these stars that things like carbon, oxygen, and iron were made. These elements later came together to form new generations of stars, planets, and eventually even life, including us. In many ways, the birth and death of these first stars were some of the most important events in the universe's history. They were like the first building blocks in the construction of everything that followed: galaxies, solar systems, Earth, and all living things. By studying these very old and distant galaxies, scientists are slowly uncovering the story of how the simple early universe transformed into the complex and beautiful place we see today. One of the most fascinating periods in this early cosmic story is called the Epoch of Reionization. This was a time when the universe went through a dramatic change. Before this era, the universe was dark and cloudy, and light couldn't travel very far. But when the first stars started to shine, their light began to ionize the surrounding gas, basically giving energy to the atoms and breaking them apart. This changed the gas from being thick and foggy to becoming clear and see-through. Suddenly, light could move across the universe more freely. This important moment helped shape the clear, star-filled sky we see today. Now, you might be wondering, how do we know all this? We weren't there, after all. The answer lies in something called redshift. Redshift is what happens to light from faraway galaxies as it travels across the vast distances of space. As this light moves toward us, it stretches out and shifts to a redder colour, because the universe is expanding. The farther the galaxy, the more stretched out the light becomes, and the older the image we're seeing. So when astronomers look at galaxies with very high redshift, they are actually looking back in time. They are seeing what those galaxies looked like billions of years ago when the universe was young. This isn't time travel like in science fiction movies, where people hop into machines and fly into the past. Instead, it's more like reading an ancient message carried by light that's been on a journey for billions of years. This light is like a time capsule. It holds clues about how the universe looked when the first stars and galaxies were just beginning to form. By studying it carefully, scientists can piece together the story of how the universe evolved, from a simple, empty space full of gas to a place filled with stars, planets, and the potential for life. It's amazing to think that the light we see today from faraway galaxies, like the Andromeda Galaxy or even more distant ones, has travelled through space for millions or even billions of years before finally reaching Earth. Every photon of light that hits our telescopes carries a piece of cosmic history. This idea makes us realise just how vast and old the universe is and how small we are in comparison. The study of redshift and ancient galaxies is one of the most exciting fields in modern science. In the next few decades, powerful new telescopes like the James Webb Space Telescope may help us learn even more. We could discover how the very first stars and galaxies came to be, how black holes formed in the early universe, and maybe, even more thrilling, if there are signs of life beyond Earth. Galaxies are enormous collections of stars, gas, dust, and something mysterious called dark matter. All of these things are held together by one powerful force, gravity. Galaxies come in many different shapes and sizes. Some, like our own Milky Way, are spiral-shaped, with long, curved arms spinning around a central core, kind of like a cosmic pinwheel. Others are shaped more like smooth, rounded balls. These are called elliptical galaxies, and they often contain older stars and look less detailed. Then there are irregular galaxies, which don't follow any clear shape at all. These often got their strange appearance from violent crashes or close encounters with other galaxies. But galaxies aren't just floating randomly through space. They are the main building blocks of the universe. Inside these giant star cities, new stars are born, live bright lives, and eventually die in dramatic ways, like exploding in powerful blasts called supernovae. These life and death cycles help shape the future of galaxies and create the ingredients needed to form new stars and planets. Galaxies also contain planets, moons, comets, asteroids, and all the other things that make up our known universe, including our own home, Earth. When it comes to size, galaxies can vary tremendously. Some are relatively small, with just a few billion stars. Others are incredibly huge, containing hundreds of billions or even trillions of stars. Our galaxy, the Milky Way, is somewhere in the middle. It holds about 200 billion stars. And here's the truly mind-blowing part. Scientists believe there are billions of galaxies scattered across the universe that we can see with telescopes. Each one has its own story, its own journey, and its own clues about how the universe began and how it continues to change over time. Every single galaxy, big or small, plays a part in this cosmic adventure. Experts think that galaxies started to form only a few 100 million years after the Big Bang, which is the term used to describe the powerful beginning of the universe. This incredible event is thought to have happened around 13.8 billion years ago. At that time, the universe was extremely hot, dense, and full of energy. The only elements around were hydrogen and helium, which are the lightest and simplest elements known. As the universe began to cool down, gravity started pulling together huge clouds of gas and dust. These clouds got denser and eventually collapsed in on themselves, creating the first stars. Over time, these newborn stars began to group together to form the very first galaxies. But these early galaxies were very different from the ones we see today. They were smaller, made mostly of hot young stars, and had very few of the heavier elements that come from older stars. Even so, these early galaxies laid the foundation for the larger, more complex ones that would grow over billions of years. Since the time of the Big Bang, the universe has been expanding, stretching out in all directions. Galaxies have slowly drifted farther and farther apart. What's even more surprising is that this expansion is not slowing down. It's actually speeding up. Scientists don't fully understand why, but it's one of the biggest mysteries in cosmology today. Meanwhile, galaxies have continued to grow and change. They crash into each other, merge, and form even bigger and more detailed structures. These cosmic interactions have helped shape the beautiful, massive galaxy clusters and star systems we see all around us today. But in recent times, a powerful new telescope has completely changed the way we think about all of this. The James Webb Space Telescope, often called JWST, has made some discoveries that have stunned scientists around the world, One of the most surprising discoveries is the finding of very old galaxies that seem to have formed much earlier than anyone ever thought possible. According to earlier theories, the first galaxies should have started forming around 400 to 500 million years after the Big Bang. That's because the universe needed time to cool down before stars could begin forming from the leftover gas. But JWST has found galaxies that may have appeared even earlier, just a few 100 million years after the universe began. Even more shocking, these galaxies look mature. They have organized shapes and show signs of active star formation. This suggests that they came together much faster than we previously believed. One of the most jaw-dropping discoveries made by JWST was a galaxy that appears to have formed only 230 million years after the Big Bang. This is far sooner than anyone expected. For a galaxy to form in such a short time, the conditions in the early universe must have been very different from what we imagined. It hints that the process of galaxy formation might have been much quicker and more efficient, or that we're missing some key piece of the puzzle. These findings are extremely important because they challenge everything we thought we knew about how galaxies and the universe came to be. If galaxies could form this fast, it means the early universe may have had special conditions, perhaps unknown types of matter, faster star-making processes, or chemical mixtures we haven't yet identified. It forces scientists to go back and rethink their models of the early universe. And what's even more fascinating is that these ancient galaxies seem to be bursting with activity. They are full of young stars being born at a very fast rate. Scientists had believed that in the early universe, star formation would be slow. That's because there weren't yet enough heavy elements, like carbon and oxygen, which are created in the cores of dying stars and are needed to form new ones. But if these early galaxies are already forming stars so quickly, it could mean two things. Either the conditions for starbirth were better than we thought, or we were wrong about how the first stars came into being in the first place. Some of the galaxies discovered by the James Webb Space Telescope are turning out to be far larger and more complicated than anyone ever expected. And what's even more surprising, these galaxies are incredibly old, dating back to a time not long after the universe first began. Scientists always thought that the earliest galaxies were small, rough, and not very developed. They believed that it would take billions of years for galaxies to become large and filled with different types of stars. But JWST has revealed a very different story. These ancient galaxies already have beautiful, detailed shapes, some even with spiral arms and well-organized structures. They are home to all kinds of stars, not just one type, showing a surprising variety and richness. This completely challenges the older view that early galaxies were simple and messy. It's like opening a history book and suddenly finding a chapter that was never supposed to exist. These discoveries have raised many new questions, especially about two of the biggest mysteries in science: dark matter and dark energy. Together, these invisible forces make up about 95% of all the mass and energy in the universe. Yet even today, scientists still don't fully understand what they are or how they work. The strange shapes and fast formation of these early galaxies hint that dark matter might have played a much bigger role than anyone realized. Perhaps it acted like a hidden framework, pulling normal matter together faster and helping galaxies form more quickly. Dark energy, which is thought to be driving the universe's expansion, might also have been stretching space in ways we never expected. The more we discover, the more it feels like we've only just begun to uncover the universe's secrets. These recent findings are so important that they could completely rewrite what we thought we knew about the early days of the cosmos. Old theories are starting to fall apart, and scientists will now need to come up with new ideas to explain how these massive galaxies appeared so quickly after the Big Bang. This is a thrilling moment in the world of science because it means that in the next few years, we could uncover more discoveries that totally change how we think about the universe's beginnings. Because of what JWST has found, researchers now have to take a fresh look at how galaxies form and evolve. That means rethinking ideas about dark matter, how stars are born, and how the entire structure of the universe developed when it was still very young. The evidence points toward an era filled with activity, mystery, and rapid changes, especially during the first few 100 million years after the Big Bang. That early time, once thought to be quiet and slow-moving, now seems to have been bursting with energy and transformation. These discoveries open the door to a whole new level of exploration. Scientists may soon learn more about how early galaxies interacted with each other. Were they more connected than we ever imagined? Did they grow by merging together, or by feeding off the energy of nearby stars and gas? These are the kinds of questions JWST is helping to answer. Another area of interest is the role of supermassive black holes, giant objects thought to lie at the heart of most galaxies. These mysterious giants might have helped shape galaxies right from the start, acting like cosmic engines that influenced how fast galaxies grew and how stars formed around them. One of the most mind-blowing discoveries in modern astronomy came from the observation of a distant galaxy known as GNZ11. This galaxy is located an astonishing 13.4 billion light-years away from Earth. That means we are seeing it as it looked only 400 million years after the Big Bang, at a time when the universe was still extremely young, just beginning to light up with stars. This makes GNZ11 one of the very earliest galaxies ever seen by human eyes. What truly amazed scientists was how huge this galaxy already was, even though it had only existed for a relatively short time. You would expect such a young galaxy to be small and still forming, but GNZ11 turned out to be packed with stars, hundreds of billions of them, making it as massive as the Milky Way, which is more than 13 billion years old and has had plenty of time to grow and evolve. Seeing such a large and complex galaxy so early in cosmic history was like finding a fully grown tree in a place where only tiny sprouts should exist. But there was more. GNZ11 wasn't just big, it was growing incredibly fast. The speed at which it was forming stars and building its structure was far greater than what scientists thought possible for such an early point in the universe's history. This rapid growth suggests that the galaxy had access to a massive supply of gas, the raw material that stars are made from, right when the universe was still in its baby years. This discovery shook the foundations of everything astronomers thought they understood about how galaxies form. For a long time, the belief was that galaxies start small and slowly grow bigger over billions of years. But GNZ11 didn't follow the rules. It seemed to skip ahead in cosmic time, becoming enormous and complex long before it was supposed to. Even more surprising was that GNZ11 wasn't alone. Other ancient galaxies, also located billions of light-years away, showed the same strange behaviour. They were enormous, filled with stars, and some had detailed, organised structures like spirals or bulges. A few even had supermassive black holes, giant objects with the mass of millions or even billions of suns right at their centres. This was a big shock because scientists thought these kinds of galaxies and black holes were something that only developed much later in the universe's history. The big mystery now was, how could galaxies grow so large and become so structured so quickly at a time when the universe was still just a few 100 million years old? One possible explanation is a process scientists call direct collapse. Usually, galaxies form gradually as gas clouds pull together under gravity, forming stars over millions of years. But with direct collapse, an enormous cloud of gas might have skipped the usual steps and collapsed quickly into a galaxy, or even a giant black hole. This shortcut would allow a galaxy to grow very fast, almost as if it had taken a leap through time. Another idea is that the conditions in the early universe were very different from what we see today. Back then, the universe was wild and energetic, filled with intense radiation, extreme heat, and vast clouds of gas. These chaotic conditions may have caused gas to clump together more quickly, speeding up the formation of stars and galaxies. It's like a cosmic storm that helped shape entire galaxies faster than anyone expected. Some scientists also think that dark matter played a key role. Dark matter is an invisible type of matter that doesn't emit light, so we can't see it, but it still has mass and gravity. That gravity might have acted like a powerful magnet, pulling in gas and helping galaxies come together much more quickly. If large amounts of dark matter were gathered in one area, they could have acted as a framework or skeleton around which a galaxy could form in record time. One of the most astonishing features of these ancient galaxies is the presence of supermassive black holes at their centres. These black holes are not the result of single stars collapsing. Instead, they are enormous, holding millions or even billions of times the mass of our Sun. And yet, they somehow formed incredibly fast, much faster than scientists had previously thought possible. Normally, a black hole takes billions of years to grow to that size. But here, in galaxies that are only a few 100 million years old, the black holes are already fully formed and gigantic. How did they grow so fast? One idea is that these massive black holes also formed through direct collapse. Instead of forming from a star, a giant gas cloud could have collapsed straight into a black hole, skipping the star stage entirely. Another theory suggests that once the black hole formed, it fed on enormous amounts of gas from its galaxy, growing at an incredible rate by swallowing everything around it. These discoveries have forced scientists to reconsider many of their old ideas about the early universe. For a long time, it was believed that the universe developed slowly and calmly, with galaxies taking their time to form and grow. But now, it appears that the early universe may have been much more exciting and full of sudden dramatic changes. It's possible that galaxies formed in a variety of ways. In some parts of the universe, they might have developed slowly, just as scientists once thought. But in other areas, galaxies may have exploded into existence at lightning speed, fueled by the intense energy, chaotic conditions, and mysterious forces like dark matter. All of this points to one powerful idea. The early universe was not a quiet, dark place slowly waking up. It was a booming, energetic time full of activity. Galaxies forming rapidly, stars lighting up the cosmos, and black holes growing at astonishing speeds. Even the period once called the Cosmic Dark Ages might not have been so dark and quiet after all. Instead, it may have been a time of brilliant explosions and fierce creation, as the first structures of the universe took shape far faster than anyone ever imagined. Most of the galaxies we see in the sky today fall into two main groups: spiral galaxies and elliptical galaxies. Spiral galaxies, like our own Milky Way, have long, curved arms that spin outward from a bright centre. These arms are made up of stars, gas and dust, all swirling around like dancers in a cosmic whirlpool. The whole galaxy moves in a graceful, organised way. Elliptical galaxies, on the other hand, don't have arms or patterns. Instead, they look more like giant glowing balls or stretched out footballs. The stars inside them don't move in neat circles but travel in many different directions, like people wandering through a crowd. These galaxies tend to be older and less active, but when scientists look deep into space, so deep that they are actually looking far back in time, they find something very different. The oldest galaxies, formed when the universe was still very young, do not look organised at all. They are messy, lumpy, and strange. They seem to be in the middle of forming rather than already shaped. This big difference in appearance comes from how galaxies form and change over time. In the early universe, just a few 100 million years after the Big Bang, galaxies were much smaller and didn't have the tidy structure we're used to. Instead of smooth spirals or clean elliptical shapes, these early galaxies looked more like cosmic puzzles with missing pieces. They were full of stars, gas and dust clumped together in uneven patches. It's as if these galaxies were caught in the act of being built, with pieces still flying into place. This chaotic look reflects the wild and turbulent conditions of the young universe. Back then, galaxies were constantly bumping into each other, merging, breaking apart and forming new structures. The universe was a busy, noisy workshop, not a quiet museum of well-arranged galaxies. For a long time, scientists believed that galaxies would slowly grow more organised and settled as they aged. They expected to find neat, smooth shapes, even in the earliest galaxies. But when astronomers began observing the farthest galaxies, the ones that formed more than 13 billion years ago, they saw something unexpected. These ancient galaxies didn't look calm or neat at all. Instead, they looked like tangled balls of stars and gas. Some were oddly shaped, with uneven lumps and jagged edges. Others looked like they were made of smaller galaxies that hadn't finished joining together yet. So, how do we even know what these ancient galaxies looked like, if they are so far away, and the light from them has travelled for billions of years? The answer lies in a fascinating trick of nature: how light moves through space. Light doesn't move instantly, it takes time to travel. The farther away something is, the longer its light takes to reach us. So, when we look at a galaxy that is, say, 10 billion light-years away, we are not seeing it as it looks now. We are seeing it as it looked 10 billion years ago. It's like looking into a cosmic time machine. If we see a galaxy that is 1 billion light-years away, then the light we are seeing left that galaxy 1 billion years ago, and we are witnessing what it looked like all the way back then. To look this far back in time, scientists use very powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope. These amazing tools can capture the faint light from galaxies that are billions of light-years away from Earth. They allow us to see what the universe looked like when it was still young and just beginning to form its first stars and galaxies. One of the most powerful tools for studying early galaxies is the James Webb Space Telescope, often called JWST. It was specially designed to look deep into space and far back in time. It can see infrared light, which is important because the light from distant galaxies gets stretched into longer, redder wavelengths as it travels across the expanding universe. JWST can pick up this ancient light, giving scientists incredibly clear views of galaxies as they looked more than 13 billion years ago. What JWST has shown us is surprising. Many of these early galaxies look far more irregular and chaotic than scientists had predicted. This discovery has challenged the old ideas about how galaxies form. Instead of slowly turning into neat, organized systems, it seems that many galaxies were born messy and stayed that way for a long time. But why were these early galaxies so messy and wild? One possible answer involves something mysterious and invisible: dark matter. Dark matter is a strange kind of matter that does not give off light or energy, so we can't see it with our eyes or telescopes. Yet, it makes up about 27% of everything in the universe. Scientists know it exists because it has a powerful gravitational pull. It tugs on the things we can see, like stars, galaxies, and even entire clusters of galaxies. In the early universe, dark matter wasn't spread out evenly. It formed dense blobs or clumps in different places. These clumps acted like giant magnets, pulling in gas and dust from their surroundings. This material then began to collapse under its own weight, forming new stars and over time entire galaxies. But because dark matter was clumped in random ways, the galaxies that formed around it didn't look smooth or regular. They were twisted and jumbled, still being shaped by the gravity of the dark matter. This may be why the earliest galaxies appear so strange. They were still under construction, shaped by invisible hands. Another reason early galaxies looked so unusual is that they were packed much closer together than galaxies are today. Back then, the universe was smaller and more crowded. Tiny galaxies floated near one another, and many of them crashed into each other. When galaxies collide, their stars usually don't crash into each other. There is just too much space between stars for that to happen. But the gas and dust inside the galaxies do crash, mix, and heat up. These cosmic crashes caused huge changes. The swirling clouds of gas and dust would get squeezed and heated, sparking the birth of new stars. Galaxies would get pulled into new shapes. Some would merge completely into bigger galaxies. Others would stretch, twist, or break apart. These violent events helped shape the galaxies into what we see today. Over time, this rough and chaotic dance gave rise to larger and more stable galaxies. But it all began in a time of cosmic turmoil. When the universe was still young, galaxies were still forming, and everything was changing rapidly. Even now, galaxies still collide and change, but it happens less often than it did in the early days. Back then, it was a regular part of the universe's wild and dramatic story of growth. Long ago, when the universe was still very young, only a few 100 million years after the Big Bang, galaxies looked and behaved very differently from the ones we see today. Back then, the early galaxies were filled with enormous amounts of gas, far more than the galaxies we see in the present. This gas was mostly made of hydrogen and helium, the two lightest and simplest elements in the universe. These gases were the main ingredients used to make new stars. Because there was so much gas flying around, early galaxies didn't have the neat and graceful shapes we often admire now, like spirals or smooth ellipses. Instead, they were wild and messy. The gas inside them was spread out unevenly, causing the galaxies to look lopsided, clumpy, and irregular. These young galaxies were like cosmic storms, turbulent, full of motion, and still trying to find their shape. Even the way stars were born in those early times was very different. In today's galaxies, like our own Milky Way, new stars usually form in special places, such as the spiral arms. These regions are organized and relatively calm, But in the early universe, star-making was much more chaotic. Stars could pop into existence almost anywhere inside a galaxy. Sometimes they were born in giant bursts, triggered by turbulence or by galaxies crashing into one another. This scattered and uncontrolled pattern of star formation gave early galaxies their clumpy and jumbled appearance. All of this happened because those galaxies were still in the process of growing up. Over billions of years, galaxies collided, merged, and matured. As this happened, they slowly began to form more organized shapes. Some turned into spiral galaxies with beautiful sweeping arms, while others became smooth and round, forming elliptical galaxies. By studying those early disorganized galaxies, astronomers can learn a lot about how galaxies grow and how the universe itself has changed over time. Deep in the center of almost every large galaxy, including our Milky Way, there lies something truly extraordinary: a supermassive black hole. These are unimaginably dense objects with gravity so strong that nothing, not even light, can escape once it gets too close. But black holes aren't just sitting quietly at the center of galaxies. They can actually shape the galaxies around them in powerful and surprising ways. Scientists believe that even in the earliest days of the universe, more than 13 billion years ago, supermassive black holes were already beginning to form in the hearts of young galaxies. Their intense gravitational pull could suck in huge amounts of gas, dust, and even entire stars. This powerful attraction didn't just affect the black hole's immediate surroundings, it could stir up the entire galaxy, making it even more chaotic. Stars might have been flung into odd orbits, and the whole galaxy could have become unstable. But black holes don't only pull things in, sometimes they explode with energy. As gas and dust spiral into a black hole, they heat up to extreme temperatures, creating enormous flashes of radiation. Some black holes even shoot out blazing jets of particles that travel at nearly the speed of light. These outbursts could punch through the surrounding space, pushing gas and dust away, and even stopping new stars from forming. In this way, black holes may have played a big role in shaping the strange and irregular shapes of early galaxies. Even now, scientists are still trying to fully understand how these cosmic giants influenced the early universe. But one thing is clear: supermassive black holes were not just silent observers, they were active, powerful forces that helped build the galaxies we see today. In the beginning, not long after the Big Bang, the universe was a wild and unruly place. Swirling clouds of gas, dust, and newborn stars filled the space, and galaxies looked nothing like they do today. Most of them didn't have smooth shapes or neat spiral arms. Instead, they looked like scattered clumps of stars and gas, without much structure at all. But over time, over billions and billions of years, something amazing happened. The invisible force of gravity began to pull everything together. Galaxies started to interact with one another, and sometimes they even crashed into each other. When two galaxies merged, their stars didn't usually collide because the space between them is so vast. But their gas and dust did interact, creating massive bursts of new stars. These galactic collisions, although violent and dramatic, actually helped galaxies settle down. The rough and messy shapes began to smooth out. Slowly, galaxies started to look more familiar. Some formed beautiful spiral arms like those of the Milky Way, while others became smooth and rounded like elliptical galaxies. Even today, this process isn't over. The universe is still changing. Galaxies continue to grow, merge, and reshape themselves. Our own Milky Way galaxy, for example, is heading toward a collision with the nearby Andromeda galaxy. This cosmic crash will happen in about 4 billion years. Eventually, the two will combine into one giant galaxy. This shows that the story of galaxy evolution is still being written. Recent discoveries have shocked scientists by showing that early galaxies were even more chaotic than anyone had guessed. These new findings are changing the way we understand galaxy formation. For a long time, scientists believed that galaxies slowly and steadily took shape over time. But now, we know the truth is much messier. The early universe was full of unpredictable and strangely shaped galaxies. Many of them looked like blobs or scattered collections of stars rather than anything structured. The forces that shaped these galaxies are still not fully understood. The conditions back then were so different from today that researchers are still trying to figure out what exactly happened. Why were these galaxies so disorderly? What caused such wild bursts of star formation? These are questions that scientists are still working hard to answer. These strange early galaxies are like the universe's first building blocks. By studying them closely, scientists can trace the history of how galaxies grow, evolve, and change over time. Each clumpy, chaotic galaxy gives us a clue about how the universe went from a wild, swirling cloud of gas to the vast, structured cosmos we live in today. One of the most exciting and mind-blowing discoveries in modern astronomy is something scientists call the earliest light, a faint glow coming from galaxies that were born only about 200 to 300 million years after the Big Bang. Imagine that. This means we are looking at light that began its journey across space more than 13 billion years ago, giving us a rare and magical glimpse into the universe's very first chapter, a time when everything we now know was just beginning to form. Back then, the universe wasn't clear and open like it is now. It was filled with a dense, hot fog made of tiny particles. In this thick fog, light couldn't travel freely. The light particles, called photons, kept bumping into other particles, getting scattered in all directions. It was as if the whole universe was wrapped in a cosmic curtain that blocked any light from shining through. But over time, hundreds of thousands of years in fact, the universe slowly cooled down and expanded. As it did, the fog started to thin out. Finally, a turning point came when light was able to escape and travel freely across space. This incredible moment is known as the cosmic microwave background, or CMB. It's a faint glow that still lingers in the universe today, a kind of baby picture of the cosmos that tells us what things looked like when it was very young. But even more fascinating is what happened a little later, between 200 and 300 million years after the Big Bang. That's when the first galaxies and stars began to form, and the first real starlight filled the universe. This starlight didn't just brighten up the sky, it completely changed the cosmos. Before this, the universe was a dark, foggy place, but the birth of these first galaxies and stars helped clear away the fog, allowing light to shine freely for the first time. This transformation is known as the cosmic dawn, the beginning of a new era when the universe started to glow with stars, galaxies, and beauty. What makes this discovery so important is that the light from these very early galaxies has been travelling toward us for over 13 billion years. That's an unimaginable distance, and yet we can detect this ancient light today, like a whisper from the distant past. This light holds incredible secrets. It tells us about the moment when the universe started to build structure, when stars, galaxies, and eventually planets began to take shape out of the chaos of the early cosmos. Scientists had always believed that galaxies began forming this early, but proving it was extremely difficult. The problem is that the farther away a galaxy is, the longer its light takes to reach us. And since these galaxies formed so long ago, their light is incredibly faint by the time it gets to Earth. Also, as the universe keeps expanding, the light gets stretched out along the way, moving from shorter wavelengths like ultraviolet and visible light into longer wavelengths, especially infrared. That makes the light invisible to our eyes. To see this stretched ancient light, scientists needed very special tools. They used incredibly advanced telescopes like NASA's James Webb Space Telescope, the Hubble Space Telescope, and some of the world's most powerful ground-based observatories. These telescopes are designed to detect infrared light, which our eyes cannot see. Thanks to these amazing instruments, astronomers were finally able to pick up the faint signals coming from the universe's earliest galaxies, signals that have been travelling across space for more than 13 billion years. One of the biggest challenges in finding this early light is the way the universe has been stretching ever since the Big Bang. As space stretches, the light travelling through it gets stretched too, so the light that was once bright and blue, like ultraviolet light, is now so stretched that it looks like infrared light, which is much redder and softer. This is why infrared telescopes are so important. The James Webb Space Telescope was specially built to look into this infrared range. It allows scientists to see things that were completely hidden before, things that happened shortly after the universe was born. This light is more than just beautiful. It's incredibly useful. It shows that galaxies and stars began forming much sooner than scientists once thought. That helps answer a big question. How fast did the universe start organizing itself after the Big Bang? The answer is faster than expected. This early starlight proves that the universe didn't wait long to start creating, and this brings us to some of the most mysterious stars of all, known as Population 3 stars. These were the very first stars in the universe. They were nothing like the stars we see today. These ancient stars were made almost entirely of hydrogen and helium, the simplest and lightest elements created during the Big Bang. What made them unique is that they had no metals, nothing heavier than helium. Because of this, they burned much hotter and faster, shining brightly for only a short time before exploding in powerful supernovae. These stars helped shape the universe by sending out energy and spreading new elements into space. They also played a key role in a major event called ionization, which helped make the universe transparent, allowing light to travel freely across space. Studying this ancient light also helps scientists understand how galaxies were built. At first, the earliest galaxies were probably small and uneven, kind of messy compared to the massive, beautiful galaxies we see today. But over billions of years, these early galaxies crashed into one another, merged, and grew bigger and more complex. This process of growth and transformation eventually led to the creation of galaxies like our own Milky Way. The very first light that ever reached us from the ancient universe has a deep and mysterious connection to two of the strangest and most puzzling things in all of space: dark matter and dark energy. These two invisible forces are believed to make up almost all of the universe, much more than the stars, planets, and galaxies we can actually see. Yet, we still don't fully understand what they are or how they work. We can't see them with our eyes or even with the most powerful telescopes, but scientists know they're out there because of the strange effects they have on everything else in the universe. Dark matter is thought to act like a cosmic glue. It helps galaxies form and stay together, using its strong gravitational pull to gather stars and gas into clusters. Dark energy, on the other hand, seems to be the reason the universe is expanding faster and faster, pushing galaxies apart more quickly over time. These two invisible forces are shaping everything, but in secret. Now, here's where the first ancient light becomes incredibly important. This light, emitted from some of the earliest galaxies to ever exist, gives scientists a rare and powerful tool for peeking into the past. By studying this light, scientists can learn how dark matter affected the universe during its earliest moments. Although dark matter doesn't shine, glow, or reflect light, it does leave clues behind in the way galaxies moved and formed in those first billions of years. The light acts like a spotlight, revealing the hidden fingerprints of forces we cannot see. Every time we discover more of this ancient light, we are peeling back the layers of time. It's as if we are looking through a magical window into the distant past. This light began its journey billions of years ago, long before our solar system existed, even before the Earth was formed. When we observe it now, it's like watching a cosmic movie showing the birth and growth of the universe itself. One of the most breathtaking discoveries so far is the light coming from galaxies that formed only 200 to 300 million years after the Big Bang. Considering that the Big Bang happened about 13 billion and 800 million years ago, this means we're seeing light from a time when the universe was still very young, a newborn in cosmic terms. These early galaxies were just beginning to take shape, and their light has been travelling across space for almost the entire age of the universe to reach us today. And this is only the beginning of our journey into the past. Thanks to incredible advancements in technology, especially the powerful James Webb Space Telescope, we can now see farther and clearer than ever before. These new tools are opening up corners of the universe that were once completely hidden. With every new piece of ancient light we uncover, we gain new clues about how galaxies were built, how stars were born, and how the universe slowly transformed into the giant, beautiful place we live in today. But this search is not just about stars and galaxies, it's also about us, our story, our beginnings. As we keep learning about dark matter, dark energy, and the early days of the universe, we're also learning about our own place in the grand story of existence. The ancient light we study today helps us understand how everything we know, including our planet, our sun, and even life itself, came into being. Picture the universe just after the Big Bang, a moment when everything we know began. It was not calm or quiet. Instead, It was a wild and fiery place filled with blinding energy, scorching heat, and swirling particles racing in every direction. Time had just started ticking, and space itself was stretching and expanding at an unbelievable speed. In those first few heartbeats of existence, just fractions of a second after the Big Bang, something strange began to happen. The matter in the universe wasn't spread out evenly. Some parts had a little more stuff crammed into them than others. These small differences, though tiny, would change the course of everything. In the areas where matter was packed more tightly, gravity became stronger. And in some rare spots, this pull was so intense that space itself may have collapsed inward, creating what scientists call primordial black holes. These black holes are very different from the ones we usually hear about, the kind that form when giant stars burn out and die. Primordial black holes didn't come from stars at all. They may have been born directly out of the raw, chaotic energy of the early universe. They could have appeared in less than 1 second after the Big Bang, making them some of the very first objects ever to exist in the cosmos. Now, here's the really surprising part. Some of these black holes could have been incredibly small, maybe even as tiny as a single proton. That's unimaginably small, but despite their size, they could have been unbelievably powerful. Inside their tiny space, they might have held the mass of an entire mountain, or even a large asteroid. Some may have contained a mass close to that of a small planet like Earth. The reason this is possible is because black holes squeeze matter into an incredibly dense form. Imagine cramming something as big as a city, or even a planet, into a space no larger than a grain of sand. That's the kind of extreme density we're talking about. These mysterious black holes are called primordial because they may have been born before anything else, long before stars twinkled, before planets spun in orbit, and before galaxies formed their elegant shapes. Some of them may have vanished over billions of years through a strange process called Hawking radiation, where black holes slowly lose energy and fade away. But others, especially the larger ones, might still be out there, quietly drifting through space. Even though we can't see them, these ancient black holes could still be tugging on stars, bending light, or even passing through galaxies without being noticed. Some scientists believe that if these black holes exist in large enough numbers, they could explain one of the universe's greatest mysteries: dark matter. Dark matter is an invisible substance that makes up most of the mass in the universe. We can't see it, touch it, or shine a light on it, but we know it's there because of the way it affects the movement of galaxies and stars. Scientists have been searching for answers about dark matter for many decades, and primordial black holes might just be the key. If we can prove that these ancient black holes exist, it could unlock secrets about how the universe was formed and how it has grown over the past 13.8 billion years. It might even help us understand how gravity works on the most basic level. Let's go back to that chaotic beginning again. In the first tiny sliver of time, less than 1 second after the Big Bang, the universe was a thick, glowing soup of particles and energy. The temperature was unimaginably high. In this hot and crowded place, not everything was balanced. Some spots had just the right mix of density and pressure that gravity took over. These rare spots collapsed in on themselves, forming small but incredibly heavy black holes. They didn't need stars to be born. All they needed was the extreme environment of the newborn universe. When most people hear the term black hole, they usually think of a giant star that has collapsed under its own weight. These are called stellar black holes, and they form when massive stars, those several times heavier than our own sun, burn through all their fuel and collapse in on themselves. These cosmic monsters can weigh anywhere from a few times the mass of the sun to dozens of times more. But there's another kind of black hole that is far more mysterious and possibly much older. These are called primordial black holes, and they might have been born in the very first moments of the universe, right after the Big Bang, more than 13 billion years ago. Unlike stellar black holes, which come from dying stars, primordial black holes didn't come from stars at all. In fact, they may have formed before stars even existed. Scientists believe that in the chaotic and fiery newborn universe, everything was packed together tightly and swirling with incredible energy. Some tiny areas had more matter than others. These denser spots might have collapsed under their own gravity, instantly becoming black holes. And so, primordial black holes could have formed naturally from the raw energy of the early universe. What makes them even more fascinating is that they could be incredibly small. Some might be no bigger than a single atom. But don't let their size fool you. Even if one is that tiny, it could still hold an unbelievable amount of mass inside. That means they would be extremely dense, far more so than anything we can easily imagine. These ancient black holes may act very differently from the ones we usually study, and that's why scientists are so interested in them. Some even believe these tiny but powerful objects might help explain one of the biggest cosmic puzzles of all time: dark matter. Dark matter is a strange and invisible form of matter that we cannot see or touch, but we know it's there because it affects how galaxies move and how light bends around them. Scientists estimate that dark matter makes up about 85% of all the matter in the universe, yet no one has ever directly detected it. It's like a hidden force shaping the cosmos, quietly pulling the strings behind the scenes. Some researchers think that primordial black holes might actually be dark matter, or at least part of it. Because these ancient black holes would be tiny, dark, and scattered across space, they would be almost impossible to see. But they still have gravity, and gravity is something we can measure. If enough primordial black holes exist, their combined gravity could help explain the invisible pull of dark matter. And that's not all. If primordial black holes really did form right after the Big Bang, they could be scattered throughout the entire universe. Some scientists even believe there might be some floating around in our own galaxy, hiding in plain sight. They would be almost invisible, completely dark and too small to detect easily, but they might still leave subtle clues. Their presence could slightly bend the light from stars or affect the way objects move through space. Even though we haven't directly seen a primordial black hole yet, scientists are searching for evidence in several exciting ways. One method involves studying gravitational waves. These are like ripples in the fabric of space and time, created when massive objects like black holes crash into each other. Over the past few years, scientists have detected several of these waves, and some of them might have come from collisions between primordial black holes. If more of these mysterious waves are found coming from unexpected sources, it could be a big clue that these ancient black holes are out there. Another way researchers search for signs of primordial black holes is by studying something called the cosmic microwave background, or CMB for short. This is a faint glow left over from the Big Bang, still drifting through space almost 14 billion years later. If tiny black holes had formed in those early moments, they might have disturbed this ancient radiation. These disturbances could leave behind special patterns or fingerprints that we might be able to detect with powerful telescopes. Primordial black holes aren't just interesting because they're old or small, they could actually help us answer some of the deepest questions in all of science. They might tell us what the universe was like in its very first seconds, when time itself was just beginning to tick. They might help explain how everything, from stars and planets to light and matter, came to be. Even more exciting, these mysterious black holes could help scientists unite two of the most important ideas in physics: Einstein's theory of general relativity, which explains how gravity works and how massive objects bend space and time, and quantum physics, which explains how the tiniest particles behave. These two theories don't always get along, and scientists have been trying for many years to find a way to connect them. Some believe that studying primordial black holes could be the key to building a theory of everything, a single set of rules that explains how the entire universe works, from the smallest atoms to the largest galaxies. Primordial black holes are like ancient ghosts, whispering secrets from a time before stars, before planets, and even before light itself. They may be the oldest things in the universe, formed when everything was still wild, hot, and new. And although they remain one of the greatest cosmic mysteries, each new discovery brings us one step closer to understanding where we came from, and what might be hidden out there in the dark. These extremely old black holes are believed to have formed during the very first moments after the Big Bang, which happened around 13,800 billion years ago. Scientists think they might be hiding important clues about how galaxies were born, the strange and invisible material called dark matter, and the hidden forces that help shape the entire universe. As our telescopes become more powerful, satellites more advanced, and scientific tools more accurate, researchers are hopeful that they will find more signs of these ancient black holes. If they do, it could bring us much closer to finally understanding whether these so-called primordial black holes are real, and what role they may have played in building the universe we live in today. The universe is so huge that it's hard to even imagine its size, and even with all the amazing discoveries made so far, there is still an enormous amount we don't understand. One of the biggest mysteries is the possible existence of primordial black holes. These are not the usual black holes that form when stars die. Instead, they might have appeared right at the beginning of everything, within the first tiny moments after the Big Bang. These ancient black holes are completely invisible, which makes them even harder to study. But they are incredibly important, because they might help us understand how the universe itself began. If scientists can learn more about them, it could help solve some of the greatest cosmic puzzles. That's why many researchers are so excited about the search for primordial black holes. To them, these hidden objects represent one of the most exciting and mysterious areas of modern science, an adventure that could finally explain how our vast and beautiful universe came to be. When we gaze into the night sky with powerful telescopes, we're not just looking at distant stars and galaxies, we're actually looking back in time. This might sound like something from a science fiction movie, but it's one of the most incredible truths about the way light travels through space. Light doesn't move instantly. It travels at a set speed, about 186,000 miles every second. That's incredibly fast, but space is so enormous that even light can take a very long time to reach us. When we look at the most faraway galaxies, the light we see from them began its journey millions, or even billions of years ago. So we're not seeing them as they are now. We're seeing them as they looked a long, long time ago, sometimes when the universe was still in its earlier stages. As scientists study these ancient galaxies, they've made a discovery that is shaking the very foundations of what we thought we knew about the universe. Inside some of these early galaxies, they've found something astonishing: supermassive black holes. These are enormous, mysterious objects with gravity so strong that nothing, not even light, can escape them. What's so surprising is not just that these black holes exist, but how quickly they seem to have formed. According to the best scientific models we have, black holes usually start off small, forming when a giant star dies and collapses. After that, they grow very slowly over millions or even billions of years, gradually swallowing up gas, dust, and even entire stars. But the supermassive black holes found in these ancient galaxies were already gigantic when the universe was still very young. That means they somehow grew incredibly fast, much faster than science currently says should be possible. Normally, black holes take a very long time to grow this big. It's a slow process, like a snowball rolling down a hill gradually gathering more snow, but these black holes seem to have skipped the slow part entirely. They were already massive, like finished skyscrapers, at a time when the universe was just beginning to build its first bricks. Some scientists think that something very special may have happened in the early universe. Maybe a strange process allowed black holes to grow much faster than they do today. Others suggest an even more mysterious idea. Maybe some black holes were born in a completely different way. Instead of coming from dying stars, they might have formed from gigantic clouds of gas that collapsed straight into black holes. Before diving deeper into this cosmic mystery, let's take a moment to understand what a supermassive black hole actually is. Simply put, a black hole is a spot in space where gravity is so powerful that nothing can escape it. Not even light, the fastest thing in the entire universe. Once something passes the black hole's invisible boundary, called the event horizon, it's pulled in forever and disappears from view. Black holes come in different sizes. Some are small, formed when huge stars explode at the end of their lives. But then there are supermassive black holes, giants that make even large stars look tiny. These can be millions or even billions of times heavier than our sun. Imagine crushing the weight of an entire galaxy into a single point. That's how powerful these supermassive black holes are. These enormous objects don't just float around randomly in space. They are found right at the centers of galaxies, including our own galaxy, the Milky Way. It's as if they're the silent rulers of their galaxies, using their invisible strength to shape everything around them. Scientists believe they play a key role in how galaxies grow and change over time. Supermassive black holes affect the movement of stars, the gathering of gas clouds, and even how new stars are born. Sometimes they release huge bursts of energy, powerful jets that shoot across vast stretches of space, changing the shape of entire galaxies. In our own Milky Way, scientists have found a supermassive black hole called Sagittarius A, sitting at the very heart of our galaxy. Even though we can't see it directly, we know it's there because of the way stars near it move. They spin around it at incredible speeds, like they're caught in a cosmic whirlpool. Despite their name, black holes aren't just empty spaces. They're among the most powerful and active forces in the universe, shaping it over billions of years. In fact, some scientists think that without supermassive black holes, galaxies might never have formed the way we see them today. Now, back to the mystery. Scientists believe that black holes start small, known as stellar mass black holes. These form when massive stars explode in events called supernovae. What's left behind is a core so dense that it collapses into a black hole. Over billions of years, that small black hole can grow bigger by pulling in everything around it: gas, dust, and even other stars. Eventually, with enough time and matter, it might grow into a supermassive black hole. But here's the shocking part. When astronomers look deep into space, which also means looking far back in time, they've found fully grown supermassive black holes in galaxies that existed less than 1 billion years after the Big Bang. This is a huge puzzle. The Big Bang, which created the universe, happened around 13.8 billion years ago. That means these gigantic black holes already existed when the universe was less than 1 billion years old. Still just a baby in cosmic terms. It's like walking into a nursery and finding a full-grown adult sitting in a crib. According to everything we understand about black holes, there simply wasn't enough time for them to grow so massive so fast. This discovery has left scientists both amazed and confused. It's forcing them to ask some very deep questions about whether we really understand how black holes grow. According to standard physics, black holes should form after massive stars die and collapse. These small black holes then grow bigger by merging with other black holes and feeding on gas and dust around them. A slow and steady process. But the black holes found in these ancient galaxies seem to have skipped all of that. They were already enormous when the universe was still very young. This brings us to one of the biggest mysteries in modern astronomy. How did these black holes grow so fast? Some scientists now believe that in the early universe something very unusual might have happened. Maybe some black holes formed directly from massive clouds of gas, skipping the star-forming stage completely. Others think these could be primordial black holes that were born in the first few moments after the Big Bang itself. If that's true, it would mean black holes have been around since the very beginning of time. And if that's the case, then we may need to rethink everything we thought we knew about the history of the universe. One of the most puzzling and surprising discoveries in modern astronomy is the existence of supermassive black holes in the early universe. These gigantic cosmic objects, some weighing millions to billions of times more than our Sun, were already present just a few 100 million years after the Big Bang, which happened nearly 14 billion years ago. This doesn't make sense based on what scientists currently understand. Normally, black holes start off small, forming when huge stars explode and collapse under their own gravity. After that, they grow slowly over billions of years by swallowing nearby gas, dust, and even entire stars. But in this case, some black holes were already fully grown giants, while the universe itself was still a baby. It's like planting a seed and finding a massive tree just a few days later. Something about it just doesn't add up. At the time these black holes were found, the first galaxies were only just beginning to take shape. Stars were still being born and there wasn't much material around for black holes to feed on. If black holes grow by eating the stuff around them, how could they have become so large so quickly when there was hardly anything there to consume? This strange discovery suggests that our current theories about how black holes form and grow might be missing something important. There could be a hidden process at work, something we haven't discovered yet, that allowed these ancient black holes to grow at lightning speed. To solve this mystery, scientists have come up with some fascinating ideas. One theory says that these black holes didn't start from stars at all. Instead, huge clouds of gas, some of them hundreds of thousands, or even millions of times more massive than the Sun, might have collapsed directly into black holes. This would mean they skipped the usual step of turning into stars first. By starting off big, these black holes wouldn't need as much time to grow into giants. Another idea is based on something called the Eddington limit. This is a kind of speed limit for how fast black holes can grow. As they pull in matter, they also give off a lot of radiation, which pushes outward and slows down how much more they can pull in. But some scientists think that, under very special conditions, black holes in the early universe might have broken this limit, allowing them to grow far faster than we thought was possible. There's also a theory about something called primordial black holes. These are black holes that might have formed right after the Big Bang, not from stars, but from the intense energy and pressure in the universe's first moments. If these black holes started off big, they would have had a major head start, allowing them to grow into supermassive black holes much earlier than usual, like joining a marathon halfway through and reaching the finish line before everyone else. Yet another idea suggests that black holes might have formed in groups, not one by one. These small black holes could have clumped together and merged with each other in the chaotic early universe. With so many collisions happening, they could have quickly grown into much larger black holes. In a short time, a bunch of tiny ones could have turned into a single, gigantic, supermassive black hole. But maybe the biggest surprise of all is that these early supermassive black holes might be telling us something entirely new about the universe, something we don't yet understand. Some scientists believe these black holes could lead to revolutionary discoveries in physics, like finding unknown forces or brand new types of matter that help black holes grow. These discoveries might even force us to rewrite some of the basic rules that we've believed for centuries. To solve this cosmic mystery, scientists are turning to one of the most advanced tools ever built, the James Webb Space Telescope, also known as JWST. This powerful telescope can see incredibly far into space, capturing light that's taken over 13 billion years to reach us. With each image, scientists are peering deep into the universe's past, back to the time when the first galaxies and black holes were forming. By studying these ancient galaxies and the supermassive black holes at their centres, astronomers hope to uncover the secrets of how such enormous objects appeared so early in the history of the universe. Every discovery brings us one step closer to solving this cosmic riddle. For thousands of years, human beings have looked up at the night sky with wonder, curiosity, and countless questions. They stared at the stars and asked themselves, is Earth the only place in this vast universe where life exists? The twinkling lights in the sky have always sparked the imagination, filling people's minds with dreams of other worlds. With billions upon billions of stars scattered across the endless cosmos, many began to believe that at least some of these stars might have planets like Earth, places where life could also thrive. For most of human history, though, this was only a dream. People imagined other Earths, but there was no proof. Scientists, stargazers, and dreamers kept searching and hoping, but they had no way to truly see what was out there. That all began to change in the last few decades of the 20th century. Thanks to powerful new telescopes and daring space missions, scientists have now discovered thousands of planets that orbit stars far beyond our own sun. These planets are called exoplanets, and their discovery has completely changed how we see the universe and our place in it. Some of these exoplanets might even have the right ingredients for life. While only a small number of them seem to have Earth-like conditions, each new discovery brings us one step closer to answering one of the greatest questions ever asked. Are we alone in the universe? Exoplanets are planets that orbit stars outside of our solar system. Some of them are rocky like Earth and might have oceans, atmospheres, or even temperatures that could support life. Others are massive gas giants like Jupiter, or strange worlds that defy what we thought was possible. Astronomers have found exoplanets in places and forms that are completely unexpected. Some are frozen in eternal winter, covered in thick sheets of ice. Others are blazing hot with entire oceans made of melted rock. There are even planets where it rains liquid metal, as the extreme heat in their skies turns iron into droplets that fall like fiery rain from the clouds. The very first confirmed discovery of exoplanets happened in the year 1992. These early planets were found orbiting a pulsar, a dead, collapsed star that shoots out beams of radiation like a cosmic lighthouse. These planets were incredibly strange and showed that worlds could form even in the most unexpected corners of the universe. Then, In the year 1995, astronomers found a planet named 51 Pegasi b. This was the first exoplanet discovered around a star similar to our Sun. It was a gas giant, much like Jupiter, and its discovery proved that planets orbiting stars like our own are real. That single discovery opened the floodgates for a whole new era of exploration. Since then, scientists have confirmed the existence of more than 5,005 exoplanets, and that number continues to grow rapidly. New discoveries are being made all the time, especially with the help of advanced space telescopes like the James Webb Space Telescope. This powerful instrument is not only spotting new planets, but also studying the gases in their atmospheres, looking for signs of life and unlocking the secrets of worlds far beyond our solar system. But not all exoplanets are alike. Scientists group them into different types based on things like size, materials, and how close they are to their stars. One of the most important groups is the gas giants. Gas giants are huge planets, much bigger than Earth. Two well-known examples in our own solar system are Jupiter and Saturn. These giants are mostly made up of hydrogen and helium, two gases that are lighter than air. Because of their size and brightness, gas giants are easier to spot in space and are often among the first planets scientists find when observing distant star systems. To get an idea of just how big they are, consider this. More than 1,300 Earths could fit inside Jupiter. These planets don't have a solid ground like Earth. Instead, they are wrapped in thick clouds of gas. As you go deeper into the planet, the gas becomes heavier and hotter. In the deepest parts, the pressure is so intense that even hydrogen, which is usually a gas, turns into a strange liquid form. Scientists think there might be a solid core at the very center, but no one knows for sure because we can't send spacecraft deep enough to find out. We know a lot about gas giants like Jupiter and Saturn because they shine brightly in our sky and have been studied by telescopes and space probes for many years. These planets also give off more energy than they receive from the Sun, which makes them stand out even more in space. Gas giants are not rare. In fact, most of the exoplanets discovered so far are gas giants. One big reason for this is that they are easier to detect. When a gas giant passes in front of its star, it causes a slight dimming of the star's light, something known as a transit. These dips in brightness allow astronomers to notice and study the planet, even if it's located trillions of miles away. Some gas giants found outside our solar system are even more extreme than Jupiter. For example, there are hot Jupiters, which orbit their stars very closely and have incredibly high temperatures. Then there are ice giants like Uranus and Neptune, which, while still mostly gas, contain more water, ammonia and methane, chemicals that make them different from Jupiter and Saturn. The discovery of so many gas giants has raised many fascinating questions. How do these giant planets form? How different can they be from one another? And is it even possible for life to exist on or around one of them? Perhaps on a moon that orbits a gas giant like Jupiter's icy moon Europa? Although gas giants seem too harsh and wild to support life as we know it, studying them helps us understand the building blocks of planets, how solar systems are formed, and what other types of worlds might be waiting out there in the great unknown. Each gas giant we discover adds a new piece to the cosmic puzzle, bringing us closer to understanding the incredible diversity of planets in the universe, and maybe, just maybe, bringing us closer to discovering life beyond Earth. Secondly, let's explore the amazing Neptune-like planets, fascinating worlds that are similar in many ways to the distant planets Uranus and Neptune, which both live far out in the cold reaches of our solar system. These types of planets are often called mini-Neptunes, because like Neptune and Uranus, they are mostly made up of gases rather than solid rock or metal. However, unlike the giant gas planets such as Jupiter and Saturn, mini-Neptunes are much smaller in size. To truly understand what mini-Neptunes are, it helps to look at their bigger relatives. Neptune and Uranus are both famous for their thick, swirling atmospheres filled with gases like hydrogen, helium and methane. This special mix of gases gives them their beautiful bluish colour and also leads to incredibly strong winds and violent storms. They're also known as ice giants because their atmospheres and inner layers contain frozen substances like water, ammonia and methane, making them not just gas worlds but icy ones too. Mini-Neptunes, while smaller, share many of these traits. Unlike Jupiter, the biggest planet in our solar system, which is a gigantic ball of gas. Mini Neptunes are much less massive. Their smaller size means they can still have thick, fluffy atmospheres made mostly of hydrogen and helium, but they don't have the super dense cores that big gas giants do. Because of this, their atmospheres are lighter and thinner, though still made mostly of gas. One of the most interesting things about mini Neptunes is that they usually don't have a solid surface like Earth or Mars. Instead, they are made up of layers of gas and ice. Some of them might have a rocky core buried deep inside, but it's hard for scientists to study these cores directly because of the thick gases that cover them. In fact, some mini Neptunes have been found with cloudy skies, powerful winds and stormy weather that make them look like smaller versions of Neptune or Uranus. Astronomers are especially fascinated by these Neptune-like planets because they appear to be quite common around other stars. So far, thousands of planets have been found outside our solar system. These are called exoplanets, and many of them fall into the mini Neptune category. Some studies even suggest that mini Neptunes could be one of the most widespread types of planets in our entire galaxy. What makes them even more exciting is how different each one can be. Some mini Neptunes have thick clouds that trap heat, making them incredibly hot on the inside. Others may have lighter atmospheres mixed with different ices and gases, leading to unique weather patterns and wild storms unlike anything we see on Earth. Even though they look like Neptune, these planets are different in other ways too. Because they are smaller, they might not have the strong magnetic fields or giant storms that their larger cousins do. But they can still be very active, with mysterious weather systems and maybe even oceans hidden deep beneath their clouds. Studying these strange worlds gives scientists valuable clues about how planets form and change over time. Every new discovery helps us understand more about our universe and raises new questions about what might be possible on other planets. As our technology continues to improve, we may soon be able to take a much closer look at these mysterious worlds. Future space missions could send robotic spacecraft to explore planets like these in detail, helping us unlock their secrets and learn even more about what kinds of worlds exist beyond our solar system. Now let's move on to another exciting group of planets, super-Earths. These are planets that are larger than Earth but smaller than Neptune. They don't get as big as the huge gas giants like Jupiter or Neptune, but they are still quite a bit bigger than our own planet. The term super-Earth simply refers to how large and heavy they are. It doesn't mean they're exactly like Earth, or that they can support life. Some super-Earths may have solid surfaces made of rock just like Earth. Others might be wrapped in thick blankets of gas or covered in icy layers. What makes them especially exciting is that some of them could have the right conditions for life. Scientists believe that if a super-Earth is at just the right distance from its star, not too hot and not too cold, there might be liquid water on its surface. And since water is necessary for life as we know it, these planets could possibly host living things, from tiny microbes to more complex creatures. Another fascinating thing about super-Earths is their gravity. Because they are more massive than Earth, their gravity would be much stronger. If a person stood on one, they would feel much heavier and find it harder to walk or jump. But this stronger gravity could also help hold on to a thick atmosphere, which would protect the surface from dangerous space radiation, something important for life to survive. Super-Earths come in many forms. Some might be ocean worlds, with water stretching from one side of the planet to the other. Others could have thick clouds and hot atmospheres, more like the planet Venus. Some may be rich in valuable minerals or contain chemicals that don't exist anywhere on Earth. Because they are so large, super-Earths might also have very active insides, with molten rock and even volcanoes. This volcanic activity could help create and maintain a stable atmosphere by releasing gases over millions of years. And if they have magnetic fields like Earth does, these planets could be protected from harmful solar winds, making them even more Earth-like and possibly friendly to life. Astronomers have already found many super-Earths around distant stars. Thanks to powerful new telescopes, we can now study them more closely than ever. Some famous examples such as Kepler 22b and TOI 700d have made headlines because they appear to be in what scientists call the habitable zone. This is the sweet spot around a star where the temperature is just right for liquid water to exist. In our solar system, there are 4 special planets known as terrestrial planets. These are Earth, Mars, Venus, and Mercury. What makes them stand out is that they are made mostly of solid rock and metal. They have strong, firm surfaces that you could actually stand on, unlike the big gas planets like Jupiter and Saturn. Those gas giants are mostly made of gas and don't have any solid ground beneath their clouds, so if you tried to land on them, you'd just sink. Because of their solid surfaces, terrestrial planets are especially interesting to scientists who are trying to find out whether other planets could support life. These rocky worlds may hold the key to discovering life beyond Earth. Earth is the most famous of all the terrestrial planets. Why? Because it's the only one we know for sure that has life on it. People, animals, plants, bacteria, everything we know that lives is right here. That's why scientists are always eager to find other planets that might be like Earth. They want to know, could there be another planet out there where life has taken root? This curiosity makes Mars, Venus, and Mercury especially fascinating to space explorers. Take Mars, for example. Often called the Red Planet, it has a dusty, rocky surface and shows signs that long ago, rivers and lakes may have flowed there. Some scientists think that billions of years ago, Mars might have had the right conditions for life. That's why space agencies like NASA have sent several robotic rovers, like Curiosity, Perseverance, and others, to drive around its surface, take pictures, dig into the soil, and search for any clues that life might have once existed there. Then there's Venus, which is sometimes called Earth's twin. That's because it's about the same size as Earth and made of similar materials. But don't let the nickname fool you. Venus is a very dangerous place. Its surface is extremely hot, even hotter than an oven, and it's covered in thick clouds filled with poisonous gases. Even though it's so different from Earth, scientists are still very curious about Venus. Studying it might help us understand how planets change over time, and why Venus became so harsh, while Earth remained a place full of life. Mercury, the smallest of the terrestrial planets, is closest to the Sun. Because of that, it has some of the most extreme temperatures in the solar system. During the day, Mercury gets so hot it could melt lead, but at night, without any atmosphere to keep the heat in, it becomes colder than an icy desert. Scientists are interested in Mercury because its surface is covered with craters from space rocks, and it gives us a good chance to study what happens when a planet doesn't have an atmosphere to protect it. What all these rocky planets have in common is that they have solid ground. That makes them different from the gas giants, and important for scientists searching for planets beyond our solar system, called exoplanets. Experts are especially interested in finding rocky exoplanets that lie in a special part of space called the habitable zone. The habitable zone is often called the Goldilocks zone, a term that comes from the famous fairy tale, where Goldilocks liked things that were not too hot, not too cold, but just right. In space, this zone is the area around a star where a planet is the right distance to have liquid water on its surface. Not frozen water, not steam, liquid water, like the kind we drink, swim in, and use for farming. This is very important because all living things on Earth, whether tiny microbes or large animals, depend on liquid water to survive. If a planet is too close to its star, like Venus, it gets way too hot. Any water would quickly boil away and vanish. It would be like standing next to a giant campfire. You'd burn up. On the other hand, if a planet is too far away, like Mars, it gets too cold. Any water would freeze solid, turning the planet into an icy wasteland. But Earth sits in that perfect middle ground. It's not too close and not too far from the Sun. This allows lakes, rivers, oceans, and even clouds to form and thrive, creating an environment where life can grow. This perfect distance from the Sun is one of the reasons Earth is so special. It allows water to move freely, and that water supports countless forms of life, from fish in the sea to birds in the sky, and of course, people. But distance alone isn't enough. A planet also needs a protective atmosphere. Think of a planet's atmosphere like a cozy invisible blanket wrapped around it. This blanket helps trap some of the sun's warmth and protects the planet from harmful space radiation and meteors. Without an atmosphere, a planet's temperature could swing wildly from freezing cold at night to burning hot during the day. That would make it very hard for life to survive. Earth's atmosphere is made up of many different gases. One of the most important is oxygen, which we breathe in every second to stay alive. Another important gas is carbon dioxide. Even though we only need a tiny amount of it, it plays a big role. It helps keep Earth warm by trapping heat. This is called the greenhouse effect. If we didn't have enough carbon dioxide, Earth could become too cold, but if there's too much, it could become dangerously hot. So, it's all about balance. Let's start by thinking about the Moon. Unlike Earth, the Moon does not have an atmosphere at all. This means there's no air to breathe, no clouds in the sky, and no protection from the harsh environment of space. Because of this, the temperatures on the Moon swing wildly between extremes. When the sun shines on the Moon during the day, it becomes scorching hot, reaching over 250 degrees Fahrenheit. But once the sun goes down and night falls, the temperature drops to an icy cold -280 degrees Fahrenheit. There's nothing to hold in the heat, and nothing to block the sun's harmful rays. Without an atmosphere, the Moon is completely exposed. It's a beautiful place to look at from Earth, but it's not somewhere life could survive. Now let's take a look at Venus. Venus is very different from both the Moon and Earth. Instead of having no atmosphere, it has one that's far too thick. This thick blanket of gas is made mostly of carbon dioxide, a gas that traps heat very efficiently. Because of this, Venus has something scientists call a runaway greenhouse effect. In simple terms, this means heat keeps building up and doesn't escape. As a result, the surface of Venus gets unimaginably hot, around 900 degrees Fahrenheit. That's hotter than the inside of a regular kitchen oven set to its highest temperature. And on top of that, the air on Venus is full of poisonous gases. With deadly heat and toxic air, Venus is one of the most dangerous places in the solar system. Nothing we know of could live there. This shows how important an atmosphere is. For a planet to support life, it needs an atmosphere with the right mix of gases. The atmosphere has to trap just enough heat to keep the planet warm, but not too much. It also needs to block dangerous radiation from space. If a planet has too thin an atmosphere, it will freeze. If the atmosphere is too thick, it will bake. Earth is special because it has the perfect balance. It's just right, not too hot, not too cold, and safe for living things. But there's another invisible hero that protects life on Earth: our planet's magnetic field. Think of it as a giant invisible shield that wraps around the Earth. This shield defends us from harmful energy that constantly pours out from the sun. This energy is called solar radiation, and without the magnetic field, it would hit Earth directly. Over time, it could even strip away our precious atmosphere, leaving us completely unprotected. Why is that so serious? Because our atmosphere does more than just hold in air. It gives us the oxygen we breathe and the nitrogen that helps keep everything in balance. It also acts like a blanket, keeping Earth's temperature steady and comfortable. If solar radiation were allowed to hit Earth without any defense, it would slowly tear the atmosphere away. Without air to breathe, without protection from the heat of the sun, Earth would become a lifeless, frozen world. Now let's turn our attention to Mars. Long ago, Mars may have had a magnetic field like Earth's, but at some point, it disappeared. Once Mars lost this protective shield, the sun's radiation started attacking its atmosphere. This didn't happen overnight, it took millions of years, but eventually much of the Martian atmosphere was blown away into space. Today Mars has only a thin layer of air, far too weak to trap heat or keep the surface safe from radiation. That's why the planet is now dry, cold, and empty. No oceans, no forests, and no signs of life. But there's something fascinating about Mars. Scientists believe it may once have looked more like Earth. It might have had a thick atmosphere, flowing rivers, and even shallow seas. Some think it may have had the right conditions for life to begin. But with no magnetic field to protect it, Mars couldn't hold on to these things. The sun stripped it bare. Today, it stands as a dusty, frozen reminder of what can happen when a planet loses its shield. This makes Earth's magnetic field even more important. It's not just a random feature, it's one of the key reasons why life is possible here. Without it, our world could have ended up just like Mars, cold, dead, and lifeless. Now let's talk about another ingredient that's crucial for life: water. Specifically, liquid water. Just being in the habitable zone isn't enough. This zone is the area around a star where a planet isn't too hot or too cold for water to exist. But even if a planet is in the right spot, it still needs water in the right form. Water in liquid form is incredibly important. It's the perfect place for the chemical reactions that life needs to begin and survive. Ice or water vapor isn't good enough. Life as we know it depends on having oceans, rivers, lakes, or even underground water flowing beneath the surface. Think about Earth. Our planet is full of life, and one big reason is because we have so much liquid water. The oceans cover most of Earth's surface. Without them, life would have a much harder time surviving. That's why, when scientists look for other worlds that might have life, the first thing they look for is signs of water. But finding water on other planets is not easy. Scientists use huge telescopes and advanced tools to look for tiny clues. They study the light from distant planets to see what kinds of gases are in their atmospheres. They look for temperatures that are not too hot or too cold, just right to keep water from freezing or boiling away. It's a tricky job, but finding liquid water gives us the best hope of discovering life beyond Earth. However, there's something else that matters when it comes to supporting life: the kind of star a planet orbits. Stars come in many sizes and temperatures, and that makes a big difference. Some stars are much bigger than our Sun. These stars are incredibly hot and bright, but they burn through their fuel very quickly. They live fast and die young, sometimes in just a few million years. That doesn't give planets orbiting them enough time for life to grow and evolve. The heat and radiation from these stars can also make conditions too harsh for life to survive. On the other end, there are smaller stars that are cooler and dimmer than the Sun. These stars live much longer, sometimes for tens of billions of years. But because they're not as hot, their planets have to be much closer to get enough warmth. If a planet is even a little too far away, it could be too cold for water to stay liquid. The best stars for life are the ones that are just right, like our Sun. Stars like the Sun are stable, warm, and live for billions of years. They shine steadily and give planets plenty of time to develop and support life. These stars offer the kind of balance that life needs. Even stars that are a little smaller than the Sun, called K-dwarfs, are good candidates. These stars burn their fuel slowly and shine for an incredibly long time, sometimes up to 40 or even 50 billion years. That's much longer than the Sun will last, and even though they're a bit cooler, they can still provide the right conditions for life on nearby planets. Exoplanets are planets that orbit stars far beyond our own solar system. These mysterious worlds can be millions or even billions of miles away from Earth. So far, in fact, that scientists cannot actually see most of them with their own eyes, not even through regular telescopes. But that doesn't stop them. Astronomers have come up with clever indirect ways to discover these distant planets. They study the light from faraway stars and how that light behaves. They also observe how stars move ever so slightly. With these techniques, they can uncover the hidden presence of planets that would otherwise remain invisible, giving us a peek into the vast and mysterious universe. One of the most popular ways scientists detect these hidden planets is called the transit method. Think of it like this. If you shine a flashlight and a tiny bug flies in front of the beam, you'll notice a brief shadow. That's exactly what happens on a cosmic scale when a planet passes in front of its star. Here's how it works. Scientists carefully watch a distant star, which could be located hundreds or even thousands of light years away from Earth. 1 light year is the distance light travels in a single year, about 6 trillion miles. These stars shine brightly, and when a planet moves across the face of the star from our point of view, it blocks a small bit of the star's light. This causes the star's brightness to dip slightly. The change is so tiny that you wouldn't notice it just by looking, but special instruments can measure it. This dip in brightness happens regularly, depending on how often the planet orbits the star. The amount of light the planet blocks tells scientists about the planet's size. The bigger the planet, the more light it blocks. By watching these dimming patterns over time, astronomers can tell that something is moving in front of the star, and that something is usually a planet. This clever method doesn't just help them find planets, it also gives clues about how big the planet is, how long it takes to orbit its star, and even if the planet might be in what's called the habitable zone, the perfect distance from the star where temperatures might be just right for life to exist. A special telescope called the Kepler Space Telescope, launched by NASA in the year 2009, used this method for many years. It kept its eye on more than 150,000 stars and discovered thousands of exoplanets. Thanks to Kepler, we now know that planets are extremely common in our galaxy, and some might even be similar to Earth. Another amazing method scientists use is called the radial velocity method, often nicknamed the wobble method. Here's the idea. When a planet orbits a star, its gravity tugs gently on the star. It's like a small child pulling on a parent's hand. The star doesn't stand perfectly still. It moves just a little, almost like a gentle wobble. This wobble is way too small for the human eye to see, but powerful scientific instruments can detect it. These instruments study the light coming from the star and notice tiny changes caused by something called the Doppler effect. You've probably noticed this effect when a car zooms by, and the sound changes as it moves, higher pitched as it approaches, lower pitched as it moves away. Light from stars does something similar. When a star moves toward us, its light shifts slightly to the blue side of the spectrum. When it moves away, the light shifts toward red. By measuring these color shifts, scientists can figure out that a planet is pulling on the star. Even if the planet is so far away that we'll never see it directly, this method lets scientists detect its presence. It can also tell them how heavy the planet is, how far it is from its star, and sometimes even what its orbit looks like. Over the years, this technique has helped discover hundreds, and possibly even thousands of exoplanets. It's like listening to the quiet footsteps of a hidden traveler walking through space. Sometimes scientists get lucky and are able to capture actual pictures of exoplanets. This rare and amazing technique is called direct imaging. But it's not easy. Stars are incredibly bright and the planets around them are much dimmer. Trying to take a picture of a planet next to a bright star is like trying to see a tiny candle flame next to a spotlight. To solve this, astronomers use special telescopes equipped with powerful technology that can block out the star's blinding light. This lets them focus on the much fainter light coming from the planet. It's like wearing sunglasses that help you see something small and dim next to something very bright. Direct imaging doesn't happen often, but when it does, it's a big deal. These rare images help scientists study a planet's size, color, and even its atmosphere. They can learn if the planet is rocky like Earth, icy like Neptune, or gassy like Jupiter. They can also look for signs that the planet might support life. Every time a new planet is photographed, it brings us one step closer to understanding the countless worlds that exist in the universe. Another incredible method used by scientists is called gravitational microlensing, and it sounds like something out of a science fiction movie, but it's very real and very powerful. Here's how it works. Gravity can bend light. So, when a massive object, like a star, passes in front of a more distant star, the gravity from the front star bends and magnifies the light from the one behind it. If there's a planet orbiting the front star, it can create a little extra blip in the brightness. This tiny flash of extra light is enough to tell scientists that a planet is there. This method doesn't require light from the planet at all. Instead, it relies on gravity and light from stars far behind it. That's why gravitational microlensing is so useful for finding planets that are way too distant or too faint for any other method. Even though it's rare and unpredictable, this technique can discover planets that no other method can. Some of the most distant and strange exoplanets we've found so far were detected this way. Imagine a lonely planet floating through the endless darkness of space. Far away, a distant star glows, sending out its light across billions of miles. Normally, the star's light travels in a straight line toward us here on Earth. But once in a while, something magical happens. If that wandering planet drifts directly in front of the star, it causes a surprising and powerful effect. Instead of just blocking the light, the planet's gravity bends it, like a magnifying glass bending sunlight. This bending makes the distant star look brighter, and sometimes even larger than it truly is. This strange effect happens because gravity isn't just a force, it also changes the very shape of space around it. That idea comes from Albert Einstein's famous theory of relativity. The heavier something is, like a planet, a star, or even a black hole, the more it pulls and twists the space around it. So, when a planet passes directly between us and a faraway star, its gravity slightly warps the light that's coming from the star. This warping creates a temporary brightening that we can see from Earth. Scientists call this amazing event gravitational microlensing. It doesn't last long, but it can reveal something we would never have seen otherwise. What makes gravitational microlensing so incredible is that it can uncover planets we can't see in any other way. Most planets are discovered by either watching how their light reflects, or by noticing how they gently tug on their parent stars with their gravity. But these usual methods don't always work, especially if the planet is very small or very far away from its star. Microlensing gives us a rare peek at these hidden worlds, even if they're light years beyond our reach. It's a bit like finding a hidden gem in the night sky. When that brief brightening happens, scientists on Earth quickly use powerful instruments to measure how much the star's light changes. From that tiny flicker, they can figure out amazing details: how big the planet is, where it is, and even how far it orbits from its star. But gravitational microlensing doesn't just help us find planets. It's also a way to discover other mysterious things in space, like black holes, neutron stars, or strange objects we still don't fully understand. Since many of the planets found using this method are located in distant corners of the galaxy or even the universe, this technique opens up a whole new way of exploring space. It lets astronomers reach farther than ever before, into places they once only dreamed of studying. Thanks to this and other advanced methods, astronomers have already discovered a number of fascinating exoplanets, planets that orbit stars outside our solar system. Some of these planets are especially exciting because they might have the right conditions to support life. Here are a few of the most promising examples. Proxima b. This planet orbits a star called Proxima Centauri, which is the closest star to our solar system. It lies just over 4 light-years away. Proxima b is located in what scientists call the habitable zone, the area around a star where the temperature might be just right for liquid water to exist. That's important, because water is essential for life as we know it. However, scientists are still trying to figure out whether Proxima b has an atmosphere strong enough to protect it and keep it livable. The TRAPPIST-1 system. About 40 light-years from Earth lies an extraordinary star system called TRAPPIST-1. This system contains 7 planets that are all roughly the same size as Earth. Even more exciting, 3 of these planets are in the habitable zone. If these planets have the right conditions, like water and an atmosphere, they could possibly support life. Because of this, TRAPPIST-1 has become one of the most closely watched systems in the universe. Kepler 442b. This planet, often called a super-Earth, is located around 1,200 light-years from Earth. It's larger than our planet, but it orbits within the habitable zone of its star. Scientists believe it might have the right temperature and possibly an atmosphere that could support life. That makes Kepler 442b one of the most interesting candidates for habitability. LHS 1140b. This rocky world lies about 40 light-years away from Earth. It has captured the interest of astronomers because it's believed to have a thick atmosphere and may even have liquid water on its surface. Its rocky terrain is similar to Earth's, making it another strong possibility in the hunt for alien life. One of the most mind-blowing and mysterious parts of our universe is something we cannot even see: dark matter. It's a strange, invisible kind of matter that acts like an invisible web, quietly holding the entire universe together. Even though we can't look at it with our eyes or take a picture of it with even the best telescopes, scientists are sure it exists. Why? Because of how it affects the things we can see, like stars and galaxies. Without dark matter, the way galaxies spin and move through space wouldn't make any sense at all. The universe would fall apart. Now, regular matter, the kind we're made of, the stuff that makes up stars, planets, and everything we can see, glows or reflects light. That's how telescopes pick it up. But dark matter is different. It doesn't shine. It doesn't reflect, absorb, or give off any kind of light or radiation. That's why scientists call it dark. Not because it's gloomy or shadowy, but because it's completely hidden. It's invisible, and yet its pull is powerful. Galaxies spin so quickly that the stars inside should be flying away into space, but they don't. Something invisible is pulling them inward, keeping them together. That something is dark matter, and it has been quietly shaping the universe since the beginning of time. To get an idea of how important dark matter really is, let's think of the universe as one gigantic puzzle. But here's the twist. Most of its pieces are completely invisible. Everything we can see, stars, planets, gas clouds, even people, makes up only about 5% of the entire universe. That means everything we've ever looked at in the night sky is just a small piece of the bigger picture. A much larger part, around 27%, is dark matter, the mysterious unseen substance that doesn't shine or glow. We can't see it directly, but it plays a huge role. It acts like a kind of invisible glue, holding galaxies together. Without it, galaxies like our own Milky Way wouldn't have their beautiful spiral shapes. Instead, stars would just drift apart, floating away into the emptiness of space. But that's not the end of the mystery. The biggest and strangest part of all is something even more puzzling: dark energy. This force makes up the remaining 68% of the universe, and instead of pulling things together like dark matter, dark energy is doing the exact opposite. It's pushing the universe apart faster and faster as time goes on. Scientists still don't know what dark energy really is, but they believe it's the force behind the universe's rapid expansion. So, when we step back and look at the big picture, we realize something astonishing. Most of the universe, more than 95%, is made up of things we can't see and don't fully understand. Yet, these invisible forces are shaping everything, from tiny atoms to giant galaxies that stretch across the cosmos. For many years, actually for more than 80 years, scientists have been chasing down the mystery of dark matter. They are convinced it's real, not because they've seen it, but because of the strange way galaxies behave. When astronomers study galaxies that are millions or even billions of light years away, they see that these galaxies are spinning too fast for the amount of visible matter they contain. According to all the laws of physics we know, they should fly apart. But something invisible is holding them together. That something is dark matter. To understand how dark matter helped shape the universe, we need to travel back to the very beginning, just moments after the Big Bang, which happened around 13.8 billion years ago. Back then, the universe was extremely hot and wild, filled with energy and tiny particles flying around in chaos. But as the universe began to cool down, dark matter started playing its part. It acted like an invisible scaffold or framework, pulling gas and dust into place and helping form the first stars and galaxies. Without it, the early universe might have stayed a chaotic mess. No galaxies, no stars, maybe even no life. Even though dark matter has played such an important role, we still don't know what it's made of. Scientists are trying to figure out if it's composed of particles we haven't discovered yet, or if it's connected to mysterious forces we haven't imagined. To solve this puzzle, researchers are using all kinds of amazing tools: gigantic detectors buried deep underground, particle colliders that smash atoms together, and powerful telescopes in space. Every experiment, every clue, brings us closer to finding the truth. But the mystery isn't solved just yet. Understanding dark matter isn't just about solving a science riddle. It could completely change the way we understand the universe. If we figure out what dark matter really is, we might also learn more about how the universe was born, how it grew, and maybe even discover new laws of physics that could change everything we thought we knew. Recently, scientists have made exciting progress, thanks to some of the most advanced technology ever built. Even though dark matter remains invisible, these discoveries are giving us better and better clues. One of the most important pieces of evidence comes from something called the cosmic microwave background, or CMB for short. This is a faint glow of energy that was left over from the Big Bang, like a baby picture of the universe. It's the oldest light we can see, dating back nearly 13.8 billion years. When scientists study this ancient light, they see tiny ripples, small patterns that show how matter started to clump together. And these patterns suggest that dark matter must have been there from the beginning, helping shape the first stars and galaxies. But how can dark matter do this if it can't be seen? The answer is gravity. Even though dark matter doesn't shine, its gravity still pulls on regular matter. It helped gather gas and dust into huge clumps, leading to the creation of stars, galaxies, and massive clusters. Without it, the universe might have stayed scattered and empty. Today, scientists are still hunting for ways to detect dark matter directly. They're not just looking at how it moves galaxies, but they're also trying to find particles or signals that might reveal its true nature. Every new discovery brings them a step closer to solving this epic mystery. In the early days, right after the Big Bang, The universe was like a giant storm of heat and energy. Everything was extremely hot, packed together tightly, and moving wildly in all directions. As it started to cool, things began to slow down and form more organized structures. But this transformation wasn't easy. Think of the early universe like a boiling soup, full of wild, swirling particles. Something had to help bring order to that chaos. That something was dark matter. Even though it was invisible, it was everywhere. And because of its strong gravity, dark matter started to clump together into huge invisible clouds. These clumps pulled in irregular matter, which helped form the very first galaxies and stars. Without dark matter's invisible hand guiding everything, the universe might never have taken shape the way it did. There would be no galaxies, no planets, no people. Dark matter was like a hidden blueprint, shaping the universe from behind the scenes. And now, billions of years later, scientists are still trying to read that blueprint and unlock its secrets. One of the most fascinating things about dark matter is how it forms something called dark matter halos. Imagine these halos as gigantic invisible clouds that gently surround galaxies like a protective bubble. They are not made of anything we can see, touch, or shine light on, but they are absolutely real. These halos help keep galaxies from flying apart. Without them, the stars in a galaxy would spin out into space and the galaxy itself would fall apart like a merry-go-round without a center pole. Scientists believe that every single galaxy in the universe, including our very own Milky Way, is surrounded by one of these mysterious halos. This idea was a major turning point in our understanding of the universe. It showed not just that dark matter is real, but that it plays a vital role in keeping galaxies together and in shaping the way they grow and move through space. In fact, without these dark matter halos, galaxies might not even exist the way we know them. One of the most important tools scientists use to find evidence of dark matter is a clever trick of nature called gravitational lensing. Here's how it works. When something incredibly heavy, like a galaxy or a big cluster of galaxies, sits between us and a more distant object, its gravity bends the light coming from behind it. This bending doesn't just change the direction of the light, it actually makes the object behind look brighter or distorted, like you're looking through a glass lens. This cosmic lensing effect is incredibly useful. It helps scientists see mass that is invisible, because dark matter, while unseen, still has gravity, and gravity bends light. By studying how the light is stretched and curved as it passes through space, researchers can map out where the dark matter must be. Time and again, they've discovered that there's way more mass in galaxy clusters than we can see with any telescope. That invisible mass is believed to be dark matter. So even though we can't directly observe dark matter, we know it's out there because it pulls on light in a very noticeable way. This light-bending effect has become one of the strongest clues that dark matter really exists. When light from distant galaxies passes through massive clusters of galaxies, the light gets bent, just like a beam shining through a magnifying glass. Scientists study these strange patterns of distorted light to figure out how much dark matter is present and where it's hiding. This has helped us draw much clearer pictures of how dark matter is spread across the universe. But that's not the only method researchers are using. They're also looking at something called the cosmic microwave background, or CMB for short. This is the faint glow left over from the very first moments after the universe was born, about 13.8 billion years ago. By analysing tiny changes in this ancient light, scientists can find more clues about how dark matter influenced the early universe. Even though gravitational lensing and the CMB give us strong hints, scientists are still chasing the ultimate prize, discovering the actual particles that make up dark matter. According to one theory, dark matter might be made of special particles called WIMPs, which stands for weakly interacting massive particles. These particles are believed to be incredibly shy. They barely interact with regular matter at all, which makes them extremely hard to find. To try to catch one of these elusive WIMPs, scientists have set up some amazing experiments. Some of these detectors are buried deep underground, in quiet places where nothing else can interfere. Others are built into giant machines like the Large Hadron Collider, a powerful particle smasher located in Europe. These experiments are designed to see if, just maybe, a dark matter particle will bump into a regular particle, creating a tiny spark of evidence. So far, no one has seen a dark matter particle directly, but that hasn't stopped the search. In fact, every experiment, even the ones that don't find anything, helps narrow down the possibilities and brings us closer to the truth. Scientists say that even the smallest clue could unlock some of the deepest secrets of the universe. Dark matter remains one of the biggest mysteries in all of science. It is invisible, but its effects are everywhere. We can see its influence in the way galaxies move, in the shapes of galaxy clusters, and in the fingerprints it left on the cosmic microwave background. All of this proves that dark matter is real and powerful, even if we don't yet fully understand it. Studying dark matter is not just about the past, it's also about the future. The more we learn about it, the more we understand the invisible forces that have shaped the universe from the very beginning and continue to shape it today. Dark matter might even be linked to another cosmic mystery, dark energy, a strange force that is making the universe expand faster and faster. By unlocking the secrets of dark matter, scientists hope to learn more about how everything in the cosmos fits together, and what might happen to it billions of years from now. And the journey has only just begun. New missions in space are opening up even more ways to study the hidden universe. The James Webb Space Telescope, launched in the year 2021, is giving scientists the clearest view ever of faraway galaxies, stars, and cosmic structures. By looking farther and deeper than any telescope before, it could help reveal how dark matter shaped the universe from its earliest days. Back here on Earth, researchers are building even more advanced dark matter detectors, some placed deep under mountains, others even floating in space. These devices are designed to catch the faintest signals from dark matter particles. With every new tool and every new discovery, we come one step closer to solving this cosmic mystery. Dark matter may be invisible, but it is one of the most powerful forces in the universe. It has been shaping galaxies and stars since the dawn of time, and while we're still only beginning to understand it, the discoveries we've made so far are incredibly exciting. The discovery of the universe's very first stars is like opening a magical window into the deep, distant past. These ancient stars, known as population 3 stars, are unlike any stars we see today. What makes them truly special is that they were made from only 2 basic ingredients, hydrogen and helium. These were the only elements floating around in space shortly after the universe was born in a powerful explosion called the Big Bang. These first stars didn't appear right away. They came to life during the universe's early, wild, and mysterious years, long before galaxies or planets had formed. Today, scientists are using the James Webb Space Telescope, or JWST for short, to search for clues about these stars. This incredible telescope allows us to look back billions of years, almost like using a cosmic time machine to glimpse moments that happened near the beginning of everything. To understand how these stars came to be, we have to go back around 13.8 billion years to the moment of the Big Bang. That was the instant when the universe began, an unimaginably hot and dense explosion that started it all. In just the first few minutes after this event, only the simplest elements could form. These were hydrogen, helium, and tiny traces of lithium. Hydrogen, which is the lightest and most common element in the universe, is made of just 1 proton. Helium comes next, with 2 protons and 2 neutrons in its nucleus. Together, these elements became the first building blocks of the universe. At that time, heavier elements like carbon, oxygen, and iron didn't exist yet. They would only be created later, deep inside the hearts of stars. In those early days, the universe was a dark and silent place. There were no stars, no galaxies, and no light, just vast clouds of invisible gas. This pitch-black chapter in the universe's story is called the Cosmic Dark Ages, and it lasted for hundreds of millions of years. It was a time of great stillness, but something powerful was slowly beginning to happen. Gravity, the force that pulls objects together, began to work its magic. Over time, gravity started pulling together the floating hydrogen and helium gas, squeezing it tighter and tighter. As these gas clouds collapsed under their own weight, they became hotter and denser. Then, finally, the first stars were born, and with them, the universe lit up for the very first time. These first stars, the population 3 stars, were nothing like the ones we see in our night sky today. They were absolutely massive, many of them hundreds or even thousands of times bigger than our Sun. Because they were so large, they burned their fuel very quickly and lived short, brilliant lives. While stars like our Sun can shine for billions of years, these giants only lived for a few million years before dying in dramatic explosions. Since they were made only of hydrogen and helium, they didn't have any of the heavier elements that stars today contain. That's why scientists gave them the special name Population 3, to separate them from younger stars, which belong to Population 2 and Population 1. The Population 3 stars did something incredibly important. They ended the darkness of the cosmic dark ages. When they began to shine, they released powerful ultraviolet light that changed everything. This light started a major transformation called cosmic reionization. Before this happened, the universe was filled with neutral hydrogen gas, which blocked light from travelling. But the ultraviolet radiation from these early stars had enough energy to knock electrons off hydrogen atoms, turning the gas into ionized hydrogen. This process made space more transparent, allowing light to travel freely for the first time. It was a turning point in the history of the universe. These giant stars may have lived short lives, but their endings were spectacular. They didn't fade away quietly. Instead, they exploded in supernovae, huge cosmic blasts that scattered newly created heavy elements across the universe. During these explosions, elements like carbon, oxygen, iron, and even gold were thrown out into space. These materials would go on to form new stars, planets, and eventually life itself. In this way, the deaths of Population 3 stars were not just endings, they were also beginnings. They planted the seeds of everything that would come after: solar systems, oceans, trees, animals, and even people. Studying these stars is one of the hardest tasks in modern astronomy. Because they are so incredibly far away, the light they gave off has been travelling through space for more than 13 billion years. By the time it reaches Earth, that light is very faint and hard to detect. Instead of seeing the stars directly, scientists look for clues they left behind. One clue is the enormous bubbles of ionized hydrogen that may have formed around them. These bubbles were created by the powerful light from Population 3 stars stripping electrons from the surrounding gas. By measuring the size and shape of these bubbles, astronomers can learn more about the ancient stars that caused them. The study of Population 3 stars isn't just about understanding the past, it's also about discovering how life began. These stars were the first to create the heavy elements needed for life, like carbon and oxygen. Without those elements, planets couldn't form, and neither could living things. By learning how these early stars lived and died, scientists can better understand how our own planet, and all life on it, came to be. Population 3 stars also help answer big questions about the universe. They played a key role in forming galaxies, black holes, and other giant structures in space. By following the story of these stars, from their birth in dark gas clouds to their fiery deaths, we begin to piece together the grand puzzle of how the universe changed and evolved over time. Each new discovery adds another piece to this cosmic puzzle, helping us see the big picture of how everything in space, including us, came to be. Thanks to the incredible power of the James Webb Space Telescope, scientists are now closer than ever to uncovering the secrets of the first stars. JWST is already giving us amazing glimpses into the early universe, and soon it may reveal even more, like how the very first galaxies took shape. Dark energy is one of the most puzzling and fascinating ideas in all of modern science. For many years, scientists have been trying to figure out what it is, but even today, it remains a great mystery. What makes dark energy so strange is that it seems to make up almost 70% of everything in the universe, but we can't see it, touch it, or measure it directly. In fact, we only know it's there because of the strange way it affects the universe around us. Let's imagine this in a simple way. Picture yourself standing in the middle of a quiet room. Suddenly you feel a strong push on your back, but when you turn around, there's no one there. You didn't see who pushed you, but you definitely felt it. That invisible push is a lot like dark energy. We don't know what's doing the pushing, but we can see how it moves things in space. To understand just how important dark energy is, think of the universe as a giant pie. The biggest slice, about 68%, is made of dark energy. Even though it's everywhere, it's completely invisible. We can't observe it with telescopes or any tools we normally use in science, so how do we even know it exists? It all began with a big surprise in the late 1990s. Two different teams of scientists were looking at very distant exploding stars called supernovae. These supernovae are like cosmic lighthouses. Because their brightness is always about the same, they help scientists figure out how far away things are in space. But when scientists measured the distance to these supernovae, they found something shocking. The stars were much farther away than they had expected. This meant the universe was not just expanding, it was expanding faster and faster over time. That was not what anyone had believed before. Until then, most people thought the universe might be slowing down because of gravity. After all, gravity pulls things together. But this new discovery showed the opposite was happening. Something was pushing the universe apart, and that something was given a name: dark energy. To understand this better, think of space as a stretchy fabric, like a rubber sheet. When this fabric expands, everything on it moves away from everything else. Galaxies, which are huge groups of stars, are like little dots on that rubber sheet. As the universe stretches, the galaxies move farther and farther apart. Scientists also compare this to a balloon. When you blow up a balloon, any dots drawn on the surface of the balloon move away from one another. In the universe, dark energy is like the air filling the balloon. It makes the whole thing grow, pushing everything farther apart. But dark energy is no ordinary force. Most forces, like gravity or magnetism, pull things toward each other. But dark energy does the opposite. It pushes things away. And here's something even more curious. It seems to be getting stronger as time goes on. That means the universe isn't just expanding, it's speeding up. Even though scientists know dark energy is doing something important, they still don't really know what it is. There are several ideas, or theories, about what it might be. One idea is called the cosmological constant. This theory was first introduced by the famous scientist Albert Einstein. At first, Einstein thought the universe wasn't expanding or shrinking. It was just staying the same size. To make his equations work, he added something called a cosmological constant, a steady energy that fills space. Later, when it was discovered that the universe really is expanding, Einstein thought his idea was wrong and called it his biggest mistake. But much later, scientists brought the idea back to explain dark energy. In this theory, dark energy is a constant invisible force that fills all of space evenly and doesn't change over time. Another idea is called quintessence. This theory suggests that dark energy is not constant. Instead, it might change from place to place or grow stronger or weaker over time. In this idea, dark energy acts like a strange kind of energy fluid that moves through the universe. Just like a magnetic field can change and shift, this energy might also be changing all the time. Some scientists even think extra dimensions might be involved. We usually think of the universe as having 3 dimensions: length, width, and height, plus one more for time. But some theories suggest there might be more dimensions we can't see. If those extra dimensions really exist, they might be affecting our universe and could help explain the mystery of dark energy. And then there's the idea of modified gravity. Maybe dark energy isn't a force at all. Maybe we just don't fully understand how gravity works over huge distances. Some scientists think that gravity might behave differently across billions of miles. If gravity is weaker than we thought in the far reaches of space, that could explain why galaxies are speeding away from each other, without needing dark energy as a separate force. One of the most powerful tools scientists use to study the universe is something called the cosmic microwave background, or CMB. This is a very faint glow of light that has been travelling through space for almost 14 billion years, ever since the moment the universe began in the Big Bang. You can think of it as the universe's baby picture, a leftover heat from when everything started. Even though it's very faint, it carries a treasure trove of information. By carefully studying tiny patterns and differences in this ancient light, scientists can learn about how the universe looked in its earliest days. These patterns help researchers figure out the shape, size, and even the future of the entire universe. Most importantly, they offer clues about how dark energy might be making the universe expand faster and faster. To investigate dark energy more deeply, scientists around the world have launched a number of major projects. One of the most exciting of these is called the Dark Energy Survey, or DES. This project uses powerful telescopes in the mountains of Chile to take high-quality pictures of the night sky. Since it began in the year 2013, DES has been observing and collecting data from hundreds of millions of galaxies across a huge area of space. By looking at how these galaxies are spread out and how they move, scientists are trying to understand how dark energy has shaped the universe over billions of years. Another major effort to unlock the secrets of dark energy is the Euclid mission, a space telescope launched by the European Space Agency in July of the year 2023. Euclid is now floating far from Earth, observing the universe with incredible precision. It is specially designed to measure the exact shapes, sizes, and locations of galaxies billions of light years away. By creating a giant map of the universe, Euclid will help scientists trace how matter and dark energy are distributed across space and time. But dark energy isn't just about understanding the past. It might also tell us something very important about the future of the universe. Right now, we know that dark energy is causing the universe to expand faster and faster. But what happens if that acceleration continues forever? One possible future is called the Big Rip. In this wild and frightening idea, the force of dark energy would keep growing stronger and stronger. Eventually, it might stretch the universe so much that galaxies would fly apart, stars would be ripped to pieces, planets would be torn away from their orbits, and even atoms might be pulled apart. Everything could be destroyed in the end. Thankfully, if the Big Rip does happen, it would likely take tens of billions of years, so we don't need to worry just yet. There's also a very different idea about the future, called the Big Crunch. This could happen if dark energy weakens over time instead of getting stronger. If that happens, the expansion of the universe might slow down, stop, and then reverse. The universe would start shrinking instead of growing. All the galaxies, stars, and planets would begin to move closer together. Eventually, everything might collapse back into one tiny point, just like at the very beginning. The truth is, no one knows for sure what will happen. Dark energy is still one of the biggest mysteries in all of science. We can't see it, we can't touch it, and we can't directly measure it. And yet, it makes up about 70% of the entire universe. It's like an invisible engine that's speeding up the expansion of space, and we're only just beginning to understand it. Scientists aren't even sure what dark energy really is. Some think it might be a kind of constant energy that fills empty space. Others believe it could be something that changes over time, or maybe it's connected to hidden dimensions of space we haven't discovered yet. What we do know is that solving the mystery of dark energy is one of the most important challenges in science today. With new space missions, better telescopes, and smarter technology, we are slowly moving closer to the answer, and one day, perhaps in the not-so-distant future, we may finally understand what dark energy is, and how it will shape the universe for billions of years to come. A biosignature, sometimes called a chemical fossil or a molecular fossil, is any kind of substance or pattern that could be a sign that life exists or once existed on a planet. This evidence might come from an element, a special kind of molecule, or even a strange pattern in the atmosphere. These clues don't have to be living things themselves. They can be leftovers or byproducts of life, like a fingerprint left behind after something was there. Scientists who study astrobiology, the science of life in the universe, depend on biosignatures to help them search for signs of life beyond Earth. These signs can show up in many different forms. For example, some gases or unusual chemical mixes in a planet's air might point to the presence of living things. In other cases, scientists might spot strange rock shapes, tiny fossils, or changes in a planet's light that could all be hints of alien life, whether it's tiny microbes or even advanced civilizations. Biosignatures are grouped into 10 major types, each one offering a different kind of evidence that life might be, or once was, there. Isotope patterns. Living things use elements like carbon or oxygen in very specific ways. When they do, they leave behind isotope patterns, versions of elements with different weights, that are very different from patterns made by non-living processes. Chemical signatures. Some chemicals, like oxygen and methane, can exist together only if something is constantly creating them. That something might be life. Organic matter. Life forms naturally make organic molecules like proteins, fats, and sugars. These can sometimes get trapped in rocks or mud and stay there for millions, or even billions, of years. Biological minerals. Some tiny life forms make minerals in ways that nature alone does not. For example, some bacteria create special crystals of magnetite, which are different from the ones made by volcanoes or other natural forces, microscopic structures. Under a microscope, scientists might see tiny patterns or textures, like microfossils or thin films of bacteria, that suggest living things were once present. Macroscopic structures. On a larger scale, scientists may find big rock formations, like ancient coral reefs or layered rocks called stromatolites, that were built by colonies of microbes long ago. Changes over time. If a planet's atmosphere or surface light changes regularly, like in cycles, it might mean life is changing it, just like Earth's plants affect our oxygen levels. Surface reflectance features. Some life forms have pigments, colour molecules, that change how a surface reflects light. These changes can sometimes be seen from space. Atmospheric gases. Gases like oxygen, methane, and nitrous oxide often come from living organisms. If we find them in the air of another planet, it might mean something alive is there. Technosignatures. These are signs of intelligent life, such as artificial lights, radio signals, or pollution. Things that could not happen on their own in nature. Not every odd pattern or strange chemical mix is a sure sign of life. To be taken seriously, a biosignature has to meet three main rules. Reliability. It must be something that is usually made by life and not easily explained by non-living processes. Survivability. It must be stable enough to last long enough so we can find it. Detectability. We need to have the tools and technology to actually notice and measure it. One big problem is that nature, without life, can sometimes copy the effects of life. For example, volcanoes or chemical reactions in rocks can sometimes release gases like methane or oxygen, tricking scientists into thinking life might be there. So researchers have to be very careful and check every other possible explanation before jumping to conclusions. One clever way scientists do this is by looking for chemical imbalances that don't make sense unless something, possibly life, is keeping them going. For instance, if a planet's air has both oxygen and methane at the same time, that's a big clue. Normally those two gases would react with each other and disappear quickly, so if both are still present, something must be making more of them, possibly some form of life. For a biosignature to be useful, it has to last long enough for our tools, like space probes, telescopes, or maybe even astronauts, to find it. One way this happens is through waste left behind when living things use energy. These metabolic byproducts are like footprints of life, showing where it has been. Also, the physical remains of life, such as fossils, can be preserved for a very long time. In fact, scientists have found fossils on Earth that are as old as 3.5 billion years. These preserved signs are some of our best evidence that life existed long ago. However, even if life leaves behind signs, we still need the right tools to find them. Sometimes, our telescopes or instruments aren't powerful enough to detect the tiny changes or signals. Life might exist, but we might miss it simply because our technology isn't advanced enough yet. Some biosignatures are easier to spot than others. For example, oxygen is one of the most promising. On Earth, it's mostly made by plants and microbes during photosynthesis, the process of turning sunlight into energy. It's also needed for many animals to breathe. Oxygen leaves a clear signal in a planet's atmosphere and is easy to detect because it affects how light passes through the air. But there's a catch. Oxygen can also form without life. A process called photolysis, where light breaks apart water or carbon dioxide, can produce oxygen. If a planet loses its water or lacks other gases, oxygen might build up in the air naturally. That's why scientists must be very careful not to mistake a natural process for a sign of life. They need creativity, careful analysis, and deep knowledge to tell the difference between living and non-living causes. And then there's the opposite problem: false negatives. This is when life really is present. but its signs are too faint or hidden for us to notice. Maybe the atmosphere hides the signals, or maybe life exists deep underground where we can't see it. Scientists are studying this problem closely, especially as they prepare for the next generation of telescopes that will study the skies of distant planets. Finding biosignatures isn't just about what's out there. It's also about the tools we use here on Earth. One issue is telescope resolution. If a telescope isn't sharp enough, it might miss subtle signs of life. Also, many telescopes and space missions are designed by large teams of scientists with different goals. Sometimes they have to make trade-offs, like choosing to study a planet's weather instead of focusing entirely on the search for life. This means some biosignatures might be harder to spot simply because the mission wasn't built specifically to look for them. Earth's own history gives us a valuable guide. Our planet has been home to life for billions of years, and much of that life has left behind chemical clues. Fields like geochemistry, geobiology, and geomicrobiology study these ancient traces, helping us understand what biosignatures really look like. Some important examples include microfossils and stromatolites. These are structures built by ancient microbes, sometimes layered in beautiful patterns. Molecular markers, or biomarkers. These are specific molecules made only by life, like certain fatty acids and alcohols. Isotopic patterns. Life tends to use elements like carbon, nitrogen, and hydrogen in ways that leave behind unusual isotope ratios. Metal patterns. Some metals, like iron, molybdenum, chromium, and rare earth elements, change their abundance or isotopic makeup in the presence of life and environmental changes. For example, by analysing the types of fatty acids in a rock, scientists can figure out which kinds of bacteria or archaea once lived there. Long-chain fatty alcohols, especially those with more than 23 carbon atoms, are signs of planktonic bacteria. Other molecules like alkanes, alcohols, and fatty acids with 20 to 36 carbon atoms often come from higher plants. These are usually found in soils and in ancient peat deposits, formed from plant waxes. Life has a way of leaving behind special clues that can tell us it was once present, even if that life disappeared millions or even billions of years ago. These clues are known as biosignatures, and they can take many different forms. Some biosignatures are chemical, like tiny bits of special molecules including DNA, fats, called lipids, proteins, and amino acids, the building blocks of life. Others are strange substances that look like kerogen, which is a kind of fossilized organic matter. Biosignatures can also appear as unusual patterns or shapes in rocks and sediments that hint at something once being alive. Tiny life forms, like microbes, are especially good at changing the environment around them. As they live and grow, they create chemical changes and leave behind marks in the materials they touch. For example, some types of bacteria can make tiny holes in carbonate rocks. Under a microscope, these holes look like little swirls or branches. They're very different from the natural bubbles or spaces found in ordinary rocks. These special patterns can be powerful hints that microbes were once there. But it's important to be cautious, because just finding a strange shape doesn't automatically mean life created it. Sometimes nature itself can make patterns that look biological, even when there was never any life involved. One of the most famous examples of this mystery comes from a Martian meteorite named ALCH 84001, ALCH 84001. This space rock was found in Antarctica and is believed to have come from Mars. Inside it, scientists discovered tiny crystals of a mineral called magnetite, along with tiny shapes that looked a lot like bacteria. At first, many experts were excited. They thought this might be real evidence of ancient life on Mars. But as time passed and more studies were done, most scientists came to believe that the structures were simply too small to be actual fossilized cells. The debate continues, even after more than 25 years, making it one of the longest-running scientific arguments about life beyond Earth. From this case, scientists learned something very important. Morphology, which means the shape or structure of something, can't be used alone as proof of life. Even if something looks like it was made by a living creature, that doesn't mean it really was. People might interpret shapes differently, and that can lead to mistakes. Today, scientists agree that to make a strong case for life, you need more than just shapes. You need chemical evidence and other clues as well. No single chemical or compound can tell us for certain that life once existed. Instead, scientists look for special patterns in organic, carbon-based molecules, patterns that only life is known to create. For instance, when living cells die and break down, they leave behind lipids, or fatty molecules, from their cell membranes. These lipids often show a very regular pattern. They're usually concentrated, have a certain size, and tend to have even numbers of carbon atoms, which doesn't usually happen in non-living chemistry. Similarly, living things only use left-handed amino acids, while random chemistry would produce a mix of left and right-handed ones. This kind of handedness could be another big clue, but biosignatures aren't always about chemistry. They can also appear as magnetic signals. Some types of bacteria leave behind tiny magnetic particles, which can be detected long after the microbes themselves are gone. Chemical biosignatures are usually made of complex molecules built from carbon, hydrogen, and other elements like oxygen, nitrogen, and sulfur. These molecules are sometimes found in things like crude oil or petroleum, where they have been slowly transformed over millions of years from ancient living material. Each biosignature has its own unique fingerprint. The slow transformation of a living matter into oil leaves behind a trail of evidence. Many of the molecules found in oil are very large, with high molecular mass, which helps scientists spot them. Some well-known examples include pristane, steranes, and triterpenes. These chemicals come from plants, especially land-based flowering plants, and are created as the original biological material breaks down over time. When scientists study oil or the rocks it comes from, they look for tiny amounts of these biosignatures using powerful tools like gas chromatography and mass spectrometry. These tools help them identify and measure the different molecules present. By doing this, they can figure out where the oil came from, how old it is, and what kind of environment it formed in. This is why biosignatures in oil are often called chemical fossils. They record the ancient history of life, locked inside molecules. These chemical clues help geologists and chemists follow the journey of oil deposits through underground layers. The exact pattern of biosignatures in a sample can reveal how far the oil has moved or whether it has been contaminated. Because these molecules are very tough and resistant to heat, pressure, and time, they're also useful in other areas, like tracking oil spills or studying polluted lubricants. Still, scientists must be careful when examining raw rock samples, since these can be contaminated or broken down by natural processes over the centuries, making it harder to get accurate results. Now, when it comes to finding life on other planets, scientists often look at atmospheres since they can hold powerful clues. Over time, life changes a planet's atmosphere in ways that natural processes cannot. Earth, for example, has huge amounts of oxygen and small amounts of methane in its air, both gases that come from living things. This strange mix is hard to explain without life. Even the colour of a planet might give away the presence of life. Life that uses sunlight for energy, like plants, often contains special pigments, which reflect light in unique ways. By looking at how a planet reflects light, scientists can guess whether it might have vegetation or something like it. This technique is called studying the planet's reflectance spectrum. Some life forms can even glow under ultraviolet light, which could be seen by powerful telescopes from space. Recently, scientists have started finding gases like hydrogen and methane in the skies of faraway planets. But just spotting these gases isn't enough. We also have to understand how the planet's atmosphere behaves. For example, finding both oxygen and methane on the same planet could be a very strong sign of life. That's because these two gases usually react and cancel each other out, so if they both exist at the same time, something must be constantly producing them, most likely something alive. Other interesting gases to look for include dimethyl sulfide and chloromethane, as well as combinations like methane and carbon dioxide. One of the most exciting recent discoveries is the possible presence of phosphine in the atmosphere of Venus. On Earth, phosphine is mainly made by living organisms, so its presence on another planet could point to life, though more research is still needed. When a planet's atmosphere is out of balance or in disequilibrium, it can be a signal that life is doing something unusual. Earth's atmosphere, for example, has been shaped and changed by life in ways that would never happen through natural chemistry alone. Since Earth is the only place we know for sure has life, scientists often use it as a model. But they also realize that alien life might be very different. It might not use the same chemicals or leave the same kinds of biosignatures we see here. That's why some researchers look for what they call agnostic biosignatures, signs of life that don't depend on Earth-like biology. They believe that all life, no matter how strange, needs energy to survive. And to get energy, there must be some kind of chemical imbalance, a condition that living things can take advantage of. By understanding the balance created by geological, non-living processes, scientists can spot when something is off, which might mean life is present, even if it's nothing like what we've ever seen before. Finding signs of life on another planet, such as a biosignature, is one of the most exciting discoveries scientists can make. A biosignature is something that hints that life, either in the past or present, may exist somewhere beyond Earth. But interestingly, discovering that a planet does not have life can also be just as important. Life depends on special kinds of chemical conditions, especially something known as redox imbalances. This happens when certain chemicals are more likely to either gain or lose electrons, creating energy that living things can use. Now, if a planet has this kind of energy-rich environment, but there's no life around to take advantage of it, that's known as an anti-biosignature. It's like seeing a dinner table full of food, but no one sitting down to eat. It tells us something valuable about the place. It could mean that life never existed there, or that something happened to wipe it out. One fascinating idea related to life is the polyelectrolyte theory of genes. This theory says that for a molecule like DNA, or any similar genetic material, to evolve through natural selection, it needs to have a special repeating structure. In the year 2002, two scientists named Stephen A. Benner and Daniel Hutter suggested that DNA, or any life-forming molecule, must be a polyelectrolyte. That means it contains repeating charge sections that help it work properly in water. Without this structure, the molecule wouldn't be able to evolve. These scientists even came up with ideas for how we might look for such genetic materials on places like Mars, Enceladus, one of Saturn's moons, and Europa, one of Jupiter's moons. One of the most debated questions in the search for life on Mars involves a simple gas, methane. Methane is important because it breaks down quickly in a planet's atmosphere when exposed to sunlight and other natural processes. So if there's a lot more methane than expected, it could mean that something, possibly life, is constantly making more of it. Since the year 2004, different spacecraft and ground-based telescopes have reported detecting methane in the thin atmosphere of Mars. The amounts found have varied quite a bit, from as little as 0.24 to 0.65 parts per billion, and in some rare spots, even as high as 45 parts per billion. These are very tiny amounts, but they still matter. However, more recent data from a very advanced instrument on board the ExoMars Trace Gas Orbiter, which was launched in 2016, told a different story. This spacecraft didn't detect any methane at all, and it set a new upper limit of only 0.05 parts per billion. That's incredibly low, so low that it seems to contradict the earlier findings. This strange difference has only made the mystery of Martian methane even more puzzling. Even more confusing is how fast the methane seems to appear and disappear. Right now, scientists don't fully understand how chemicals behave in Mars' atmosphere. The way methane comes and goes so quickly doesn't match any current model of how gases are supposed to break down. To really solve this mystery, scientists would need to send a lander or robot with a tool called a mass spectrometer. This instrument could study the kinds of carbon atoms in the methane, especially carbon-12 and carbon-14. By comparing the amounts of these carbon types, scientists could figure out if the methane came from living organisms, just like they do here on Earth. There's another piece of the puzzle too. Mars's atmosphere contains a lot of carbon monoxide and hydrogen, two gases that are full of potential energy. On Earth, microbes and other life forms would quickly use up these gases as fuel, but on Mars they seem to just hang around in the air unused. This is another possible anti-biosignature, because it suggests that no life is present to take advantage of the available energy. To some scientists, this could be a clue that life is either not there or has not yet been found. The science that explores life in space is called astrobiology. At its heart is the belief that if life exists beyond Earth, we might be able to recognize it through the clues it leaves behind, like biosignatures. But for a biosignature to really count as proof of life, it must be something that living things are likely to produce, and something that natural non-living processes, known as abiotic processes, are very unlikely to create. To confirm that a biosignature truly comes from life, scientists have to rule out every other possible explanation. Like all major discoveries, finding real evidence of alien life will take time, many experiments, and a lot of careful analysis. Back in the 1970s, NASA made history with its Viking missions to Mars, which were the first to carry out experiments designed to search for signs of life on another planet. The two Viking landers each had 3 different experiments to test whether life, especially microbial life, might be present. They looked for things like metabolism, but unfortunately the results were unclear. Some tests gave hints of something interesting, but others did not, leaving scientists with no final answer. Today, NASA's Curiosity rover is still hard at work on the Martian surface. It is part of the Mars Science Laboratory mission, and its job is to explore whether Mars could have supported life in the past, or maybe still can. Curiosity is equipped with many tools that can search for signs of life, such as organic molecules, possible microbial remains, ancient chemical patterns, and special gases that might have been produced by living things. It focuses on areas where organic matter might be preserved in rocks, which improves the chances of finding ancient fossilized life. At the same time, the ExoMars Trace Gas Orbiter, launched in 2016, continues to study Mars from above. It is mapping where gases like methane come from, and this information is helping scientists decide where to land future missions. One of those missions is the Rosalind Franklin rover, named after the famous scientist who helped discover the structure of DNA. This rover was planned to launch in 2022, and it will be able to drill as deep as 2 meters below the surface of Mars. That's important because under the surface, any signs of life could be better protected from the harsh radiation that hits the planet's surface every day. Another mission, called the Mars 2020 rover, also known as Perseverance, launched in the year 2020. Its goal is to study parts of Mars that may once have had the right conditions for life. It is exploring the rocks, soil, and ancient environments of the planet to find out more about its history and whether it was ever habitable. Perseverance is also collecting rock and soil samples that could one day be brought back to Earth, where scientists can study them with even more powerful tools than those sent to space. When we look beyond the planet Mars in our search for life, one exciting mission that stands out is NASA's Dragonfly mission. This mission is planned to launch in the year 2025, and it will head toward Titan, the biggest moon of the planet Saturn. Titan is a fascinating place because it has a thick atmosphere filled with complex carbon-based chemicals. Scientists believe that Titan may have the right conditions for early forms of life to begin, or for what is known as prebiotic chemistry, the kind of chemistry that might have happened on Earth before life actually started. The Dragonfly spacecraft is not just going to fly past Titan, it will actually land there and explore its surface and skies. It will search for biosignatures, which are signs that life might have existed in the past, or could even exist now. By flying from one location to another like a drone, Dragonfly will study the moon's atmosphere, the icy ground, and the mysterious organic materials that cover it. The hope is to find out whether Titan, even though it is so far from the sun and extremely cold, might still be a home for life. Another amazing mission is the Europa Clipper, which will explore Europa, one of the smaller moons orbiting the giant planet Jupiter. This spacecraft is set to launch in October of the year 2024, and it is expected to arrive at Europa in April of the year 2030. Instead of landing, Europa Clipper will fly by the moon many times to collect data. Its main goal is to find out if Europa, which is covered in thick ice, could have an ocean of liquid water underneath, and whether that ocean could support life. Scientists are especially interested in Europa because they believe that underneath its frozen surface lies a huge salty ocean. In fact, this hidden ocean might contain 2 to 3 times more water than all the oceans on Earth combined. Here's some of the evidence that supports this exciting idea. In the year 1979, NASA's Voyager 1 spacecraft took the first close-up pictures of Europa. The images showed strange surface features that looked like cracks or ridges, similar to what we see with tectonic activity on Earth. Scientists thought this might be caused by an ocean below pushing and shifting the ice above. In 1997, NASA's Galileo spacecraft noticed a small change in Europa's magnetic field as it flew past. This was taken as a strong clue that something conducting electricity, like a salty ocean, was hiding under the ice. Then, in 2012, the Hubble Space Telescope captured something astonishing: a giant plume of water vapour erupting into space from Europa's surface. This suggested that water from the ocean below might be escaping through cracks in the ice. The Europa Clipper will carry special instruments to investigate further. It will try to confirm if the ocean really exists, find out what it's made of, map the icy surface, and search for any signs of activity linked to that deep ocean. All of this could help us answer the big question: could life survive in such a place? Now let's talk about another moon with a hidden ocean, Enceladus, a small moon orbiting Saturn. While there isn't a mission yet that's specifically designed to search for life on Enceladus, this little moon has shown some amazing signs that make scientists very curious. In the year 2005, NASA's Cassini spacecraft spotted jets of water vapour shooting out from cracks near Enceladus's south pole. These geysers were later found to contain salt and organic molecules, the kinds of chemicals that life might need. Then in 2014, more detailed measurements supported the idea that a huge underground ocean exists beneath Enceladus's icy shell. Because of all this, many scientists hope that future missions will visit Enceladus and look for signs of life there too. But what about life outside our solar system? The closest potentially habitable planet beyond our Sun is called Proxima Centauri b. It orbits a star that is only 4.2 light-years away. In space terms, that's actually quite nearby. But even at that short distance, using today's spacecraft technology, it would take more than 18,000 years to reach it. That means we can't visit it anytime soon. Instead, scientists use powerful telescopes to study planets like Proxima Centauri b from afar, hoping to spot signs that life might exist there. So far, scientists have not yet found any confirmed signs of life on exoplanets, planets outside our solar system. However, this field of research is growing fast. A big step forward came in December of the year 2021 when NASA launched the James Webb Space Telescope. Although the Webb telescope can't detect certain key gases like oxygen in the atmospheres of exoplanets, it can still spot clues, such as chemical patterns or temperature changes, that might hint at life. Looking toward the future, new telescopes being built on Earth, like the 30-meter telescope and the extremely large telescope, will allow scientists to study the atmospheres of distant planets in much greater detail. These massive telescopes will be able to separate real signs of life from false positives, such as oxygen that might be produced by things other than living creatures.